Hey guys, it's John here, and in this video, I'm going to go over everything you need to know for the SAT geometry section. This video is going to cover every major topic that you are going to see on the SAT for geometry questions and how to solve each one in detail. If you want to know why you can personally trust me, I've scored a 1550 on the SAT. I currently own the largest SAT Skool community on the Skool platform right now, and my goal is to make the YouTube channel you're watching right now the best SAT YouTube channel in the world. Okay, one thing I should say before we get into this is that this video is going to go over a lot of information. But the way you should think about it is this. It's not the information in these videos that's going to help you improve your score. It's the application of this stuff. Many people think that there's some kind of magical secret way to improve your SAT score. I can just tell you, first of all, there's no secret way that's just going to automatically improve your SAT score overnight. But probably the closest thing you can get to that is not just watching these videos, but watching them and also doing problems based off the material in them. So in this video, you're going to see a lot of different SAT practice problems based on each of the content within each lesson. I want you to actually pause the video every single time I show a practice problem and try it on your own before you watch the video. This may seem kind of obvious, but I often forget to tell students to do this, so do it if you aren't right now, and that's going to really supercharge your learning as you go through this. First thing on the docket, we're just going to go over some of the basic geometry things, so stuff involving lines, angles, triangles. In this video, I'm going to explain all the basic rules you need to know for SAT geometry and how to actually use it in practice. So the first thing you should know going into this, I kind of hinted at this already with the intro, but basically the way you should think about this is you really need to know this stuff for all of the geometry questions. If you don't know this stuff, it's kind of like if you're trying to learn physics, but you don't know basic math. It doesn't matter how many different physics textbooks you look at, you're always going to be absolutely cooked because you won't know just how basic math works, which is what all of physics basically relies on. So you must know this stuff. I'm going to give you a bunch of different key rules to know for SAT geometry, and then we're going to go through some practice problems on it. Okay, the first thing you need to know for SAT geometry problems is this rule with two angles on either side of each other. A lot of SAT tutors say, okay, this is like the vertical angle rule, this is the complementary angle. I really don't care about any of that stuff. All I care is that you actually know what it looks like and how to use it. It doesn't matter if you know the exact name of it or not. It really does not matter to me at all. Okay, so just to get something out of the way, what an angle is basically the distance that two different lines can be spread apart from each other. So for the example, this one is a 40-degree angle. The unit for angles is the degree, like degrees, like Fahrenheit, but not like that. Degrees in a different kind of way here. If you've ever used a protractor, you should definitely know what an angle is. Okay, if you have two angles like this that are just on the exact opposite of each other, and you have two lines that are just perfectly crisscrossing like this, these must be the exact same angle. This is the simplest possible geometry rule, but it makes everything else so much easier. What you can't have is something where like one of the lines is like bent in the middle. So if it's something like this, then of course this angle would not be the same as that angle. You can tell just by looking at it, this one is much bigger than that one. But if they are exactly perfect like this, they're both straight lines, then you can use this. In addition to that, you can know that whenever you have a straight line like this, the angles on it must add together to 180 degrees. So if you are somewhat good at math, you would know 40 plus 140 equals, you guessed it, 180. And that makes sense because they are both on this line. So if you have a line like this and just any kind of angle coming off of it, you know these added together must always be 180 degrees. Same thing for over on this side. I just wrote all of them so you can see every single angle over here. Now, in addition to this, you can have a situation where you have one line passing through two parallel lines. When I say parallel, what I mean by that is that they basically are just perfectly matched up. So this line is the exact same angle as this line. They are both just perfect on this. Hopefully you know what parallel is, like parallel parking. If you have a car and you have the curb like this, you're trying to park the car basically in this configuration to the curb. You would not want to be parking like, this, as I sometimes do because I really am bad at parallel parking. So that would be not parallel and this would be parallel. So if you have two lines that are like that and you have one line going through them, you know these two angles must be the exact same as well. You can kind of just logically tell this, like, yes, these look pretty much the exact same angle, but it's actually also true based off of geometry. And then the final thing is kind of bringing all this stuff together. If you have two parallel lines and you have a line going through them, you would know that these must add together to 180. These must also add together to 180. But in addition to that, you can take this angle and say it's the exact same thing as this angle up here. These both must be 70 degrees. And likewise, these both must be 110 degrees. The thing to know about all four of these things is that it just always must be true. Many people are confused with geometry questions, whether they can make, an assumption, whether they can assume that this angle is what it looks like, these are the only cases where you actually can make that assumption. You actually can just look at this and say, okay, that angle is the exact same as that angle. It must, in fact, be the exact same measurement. These both look the same. They must be the same. But these are the only times you can do this. You cannot just assume that an angle must be something because it looks like a certain amount. For any situation not described here, you must actually have the angle measurement listed in order to make these kinds of assumptions. Might be kind of obvious, but trust me, many students, it's not that obvious for. Just trust me here. Okay, now onto some shapes. What a shape is, in case you skipped preschool, I guess, is a group of lines where they're all enclosed. We see here, this is a triangle. If it was not enclosed, it would look something like this. You can see there's this big hole at the top. That would not be a shape. Okay. Big thing to know with triangles is, first of all, when you have the interior angles of the triangle, aka the angles on the inside of it, they must add together to 180 degrees. Very, very simple here. But one thing you may not realize is that this is also a rule for other shapes as well. For example, if you have a square, something like this, and you're trying to find the amount that the interior angles of this must be equal to, you can use this exact formula, 180 multiplied by n minus 2. In case it wasn't obvious, n is the amount of sides of the shape. And so you can use this formula on literally any shape imaginable to figure out what the interior angles must equal to. If you want to confirm it on this triangle here, just think about it. The triangle has 1, 2, 3 sides. 180 times 3 minus 2 would equal 180 times 1. 180 times 1 is equal to, you guessed it, 180. I know this must be completely mind-blowing to all of you. Likewise, if you were to look at a square, it would be 180 times n minus 2, 180 times 4 minus 2, because there are 4 sides to a square. 180 times 4 minus 2 would be 180 times 2, which would be 306 degrees. And you guessed it, yes, if you add together the interior angles, 90, 90, 90, and then also 90 up here. So it must add together to 360 degrees. If we even have a shape here like a pentagon, pentagons have 5 sides. We could do here 180 multiplied by 5 minus 2. That'd be 180 times 3, which according to Desmos is 540. So if you add everything here, you get 540 degrees. Okay, I know for some of you, this was like the most basic, easy stuff imaginable. Let's just go through a few more rules and we'll finally get to some good practice problems to test you on this stuff. In addition to that stuff, another thing I must tell you is that when you have an equilateral triangle, aka a triangle where all these sides are the exact same measurement, you must have the same angle measurements as well, which would just be 60 degrees, 60 degrees, and 60 degrees. Because if you divide 180 by 3, it must inherently be 60 degrees. So just know this, equilateral, same sides, but also the exact same angle measurements in every single part. You can also, though, have an isosceles triangle. This is where these two sides are the exact same, but this one is something different. When you have an isosceles triangle, these two angles over here must also be the exact same, so they can both be 80 degrees. So if you know just one of these angles, you know what the other one must inherently be as well. And one more quick small rule, if you have the exact same angle measurement, these would be considered congruent angles. I talked about this a little bit in my similar triangles video because this also has a really important thing with that. But yeah, same angle measurements means congruent angles. That's just the term for it. And then just finally here, we have exterior angles. So if you have a configuration like this with a triangle and then one line just jutting off from it, you know that this angle must equal these two other angles added together. C must equal B and then also A. Also just surprisingly useful in some random problems. Big thing to know here is that C is not equal to this angle. This one is completely not important, not useful at all, but you can know that these together would add up together to 180 degrees according to that rule above. But besides that, this one is not important. You just look at the ones that are not right connected to that angle. Now, I'll be real, I can definitely imagine some of you watching this video up until this point and think to yourself like, bro, we know this stuff. Like, we know that this is how this stuff works. You're not giving me any new information here. And yes, I completely agree with what you're saying. For many of you, this might not be new material. But before you fully say that, just make sure that you can solve these questions, because I have talked to many students who maybe would have told me that they understood everything I went over here, but then if they get shown a question like this, they just suddenly have no idea what to do. Because with a lot of these SAT geometry questions, what happens is you're getting some kind of weird configuration like this, and it's kind of like a puzzle. Like, you get given these different pieces of information, and you have to figure out what can you do with the unknown stuff like this JKL here to figure out what the answer would be. And oftentimes it just comes down to playing around with stuff, just seeing what works where, trying it out, and just seeing when you can find the right answer. You may think that there's a much more complicated thing than that, but that's honestly just how I solve these problems, so just follow this exact thing. Also, what's going to be important here is writing equations for a lot of this. We went over some examples where, the angles must equal, for example, 180 degrees or just equal what the other one is. In these cases, you can just write, for example, 140 plus, let's say if we didn't know what this one was, we could just say 140 plus x1 equals 180. that would be a potential equation you could write for these problems. And so I'm going to be writing a lot of those with these. Okay, enough talking about this. Let's actually go ahead and solve this problem. So we have here, we're trying to find what JLK is. All this information is just describing what we have here. So pretty easily, we can just see here that we have this thing, and that thing. They must add together to 180 degrees because this is a triangle. So I can do 45 plus 2x plus 5, parentheses on that, just in case, plus y. I'm going to use y to describe that one, and that must together equal 180 degrees. Okay, so that's pretty good, but if you've watched my other videos before, you would know you must have the same amount of equations as you have variables. We have here 2 variables, but only 1 equation, so we need another equation somehow, or else we cannot solve the problem. So an easy one we can do, we see this straight line over here, so therefore 4x plus 20 plus y, which is what JLK must be, would just equal 180 degrees as well. This is the other rule with the straight line and then the angle coming off of it. Unbelievable stuff we have here, that the thing must be 100 degrees, which yes is the right answer. We know that it's 100 and not 15 because we're looking for y here, which is what JLK is. See if you can solve this one. I'll admit some of the angles and the thing that went with them got kind of cooked, so I just drew these lines with them, but everything else is pretty simple. Okay, big thing that may jump out at you here is we have 2 parallel lines. And so you're probably thinking back to these rules I went over here and over here. And yes, we do have to use those rules. So think about this for a second. We have, wait, not that one. We have this whole big angle here, which is 132 degrees, and this smaller one, which is contained within the bigger one, which is x plus 8. We also have this angle, which is 3x plus 4. If you think about it, though you kind of have to contort your head a little bit to see this, what this basically is just 2 parallel lines and 1 line going through them. That is basically what is going on here. So with that information, we know that this angle, specifically this one over here, not the entire thing, would be equal to this angle. It's basically like we have 2 parallel lines, and then we have this A to D, which is going through them like this. In this case, this angle would equal this angle, and then this angle would also equal this angle. So let me just go ahead and write some equations. We know this whole thing must be 132, but we don't know what this angle specifically is. In order to find that, we could just say 132 minus this annoying x plus 8. So now we have just this angle BAD. And then that must be equal to 3x plus 4 because we just have this angle over here. Since there's only one variable in this, I can just put 1 and 1 and then just put a tilde, and that gives me the answer being 30, which yes is the right answer. 3, so we have some other stuff here. First thing we can very clearly see is this is a triangle, so 180 degree rule. We can just say here 3k plus 10 plus 55 plus w would be equal to 180 degrees. But again, we have 2 variables here and only 1 equation, so we need another equation in here somehow. You can probably tell this is going to involve the 180 degree rule when you have a straight line. So we have here that 7k minus 5 plus 55 plus this random angle over here would add together to 180 degrees. Now, what would be this random angle over here? Well, you can probably tell based off what I've been explaining so far that you have to use this parallel line rule again. And so using the parallel line rule, you can imagine it's kind of like this, and you have 2 parallel lines here. Again, I know they don't look exactly parallel, but that's fine. And so in that case, if you imagine this thing would be like over here, this thing would be over here, and those would be the exact same angle. So therefore, we can basically just say plus 3k plus 10. That is what this angle is. It's just this exact one. And that must equal 180. As you may know, if you know anything about Desmos, you do have to use x and y when you're writing a system of equations like this. So I'll use x for k and then y for the w. So x there, x there. We get this kind of configuration, 12 and 79. 79 would be the right answer because we're looking for w here, which is my y. So therefore 79. Okay, moving right along here. So let's get rid of some of the parallel stuff and talk about some of the other rules for a second. So this is a very sneaky problem, I will be honest, because there's a few things that kind of feel like trick questions here. The first of those is the fact that you have y here and z. So this literally just be the exact same angle. Like the rule still applies here, even though they're trying to make you feel like it's something different. So we just know that this has to be y. So okay, we avoided their trap there. It just is y and y again. Second thing that you may notice if you look at this hard enough is these are both isosceles triangles as shown by these 2 hatch marks in each one. They are the same side measurements for each of these and each of these. Therefore, the angle measurements at the bottom must be the exact same as each other. So this would also be x. But, you know, just think about it again, this would also be y. So therefore, this triangle is basically the exact same, or at least it's similar to the other one. So these would also be x, and x, because they must add together to 180 degrees. So if we know that these are the exact same and this is the same angle as there, we know it just must end up being the same measurements. With this information, it is very, very easy to just write a couple of quick equations. First one here, 2y equals z plus 30. We know that z is equal to y, so we can just say 2y equals y plus 30. Amazing. Technically, we could just use that to solve the problem, but I'll just go ahead and write another equation regardless. So y plus x must also equal 180 with the triangle rule. So therefore, we see here 75, 30. So the answer would in fact be 75, because that's the x value. Just a quick thing that I should mention, the isosceles rule is one of the sneakiest things on the SAT for the geometry, because it never really jumps out at you, and it's just like a thing that can sometimes show up, like they just randomly say, oh, this is isosceles, and you have to just remember, oh wait, you have the same angle measurements here as well. So just keep that in mind. It's something that many students miss the first time they go through a problem like this. So, okay, we have some more triangles here. So we have these two intersections over at this point E, and then we're trying to figure out what x would be. So you can probably guess what I'm about to do here. I'm just going to set a variable for this thing here, and it would be the exact same variable for both. Okay, pretty simple stuff there. In addition to that, we have an isosceles situation again. Again, probably did not jump out at you as first, unless you really are thinking about isosceles now, so keep that in mind. Good thing to know. 58 degrees would also be the measurement over here. With this information, we have more than enough to solve the problem, because we can just say here y plus 58 is equal to 180 for this thing over here. Just put y1 there instead and tilde, so we get 64 would be equal to y. But that's not what they're asking for. They're asking for x. So we know that this would be 64, and we can then write 64 plus 47 plus, I'll say x1 regardless, equals 180. Therefore, x would be 69. Good stuff there. Last problem for this video, we have here two triangles yet again, and we have some parallel information, that kind of stuff. We can just know here, first of all, that this would also be x, and then it's actually literally that simple. We can just say x1 plus 42 plus 53 would be equal to 180. Kind of shocking it's that simple, but yes, it is. One more thing I just want to quickly mention on this is this thing called the triangle inequality theorem. I'm pretty sure you're not going to really ever see this on the SAT, but in the small chance you do, it's just this very simple rule that the sum of the lengths of any two sides of a triangle is greater than the length of the third side. So this can work in any kind of way you can imagine. So a plus b for this triangle would be greater than c, a plus c is greater than b, and b plus c is greater than a. So all of these must work. So it's kind of like an interesting rule, just kind of a interesting factoid about triangles, but you could see a problem like this. In a triangle, the lengths of two sides are 9 and 14. If the length of the third side is an integer, so like a whole number, what is the greatest possible perimeter of the triangle? I say what a perimeter is in a different video, but just so you know, going into this, the perimeter is the lengths of all the different sides of a shape added together. So if this side has the lengths 3, 4, and 5, the perimeter of this would be 3 plus 4, 7 plus 5, so 12 would be the perimeter of this triangle. Okay. With that out of the way, we have here that 9 and 14 are two of these sides of it. So we have a triangle like this, 9 there, and then 14 over here. What could be this third one over here? Well, basically what we know from this is that these two sides must be greater than that third one. So 9 plus 14, I'll just tell you to save us the Desmos, is equal to 23. So therefore, this one must be 22 or less. If it's 23 or greater, it would violate this rule because it would be equal to rather than this one being greater than that one. So 22 or less, therefore the largest perimeter would be, if it is 22, because that's the biggest we can go for, 9 plus 14 plus 22 would be equal to 45. Again, if you can't do that off the top of your head, just use Desmos, but that's what the answer would be. Just a very simple rule here, not really too much else you need to know about this exact thing. Second up, we're going to talk about right triangles. Okay, how do you solve SAT right triangles problems? I honestly think this might be one of the best SAT right triangles videos on YouTube, because I'm going over everything you need to know in this video. Literally every single major formula, every single concept, every single technique going to be covered in this video for right triangles on the SAT. And this is pretty important because this is by far the most common thing you're going to see in geometry problems on the SAT. Right triangles are everywhere on the test, and if you do not know how to solve these questions, you are just absolutely cooked. Now, first of all, what is a right triangle in the first place? Well, triangle, if you do not know, if you're really new to this stuff, is a shape that has three sides to it. So this would be a triangle. Right, though, means that there is a right angle within the triangle. What a right angle is a 90-degree angle. And if you don't know what an angle is in the first place, well, okay, you're probably really new to this then, but it's basically this. It would be the space between two lines that are at a, well, I don't want to use the word again, but that are at an angle to each other. So this here would be an angle. When that angle is equal to 90 degrees like this, that would be a right angle. A right angle also always appears perpendicular, so it has like an L shape to it, one right upright, the other line is immediately to the east, essentially. So that's what a right triangle is. It's going to be a triangle that looks kind of like this because it has 3 sides and also it has a right angle over here. It cannot have more than one right angle, otherwise it is not a triangle anymore. Okay, so there are 4 main things you need to know involving what you can do with right triangles when you see it on the SAT. What I really want you to do is whenever you see a right triangle on the test, just think to yourself which one of these rules could work. Because it's almost always going to be one of these 4 things, and it's just up to you to figure out which one will apply to the scenario, though it sometimes can be more than one as well. Okay, first thing here, this is the most common Pythagorean theorem. This happens all the time, and the reason why it's so common is because all you need to use this is side lengths of the triangle. It does not matter at all the angle measurements, though it can only be used on right triangles themselves. Okay, what the Pythagorean theorem is basically if this side is A, and this side is B, and then this side is C, A squared plus B squared must be equal to C squared. That is literally it. The lengths must add up together in this formula. A and B, it doesn't even matter where they are. All that matters is that they cannot be the longest side of the triangle. The longest side must be C, but for the other 2, it doesn't even matter. I could just make this one A and this one B if I wanted to. I can make opposite. Doesn't even matter. Just A squared plus B squared, whatever those are, must equal C squared. Always also remember to have the squared at this as well. If there's not a square, it's going to mess everything up. It's not going to work. So the way this can be used, if you, for example, just have 2 of the side lengths, like if you know this is 1 and this is 2, you can just plug it into this formula. What that would look like would be this: 1 squared plus 2 squared, and then tilde, this also means equal sign, C squared. And then we see here C must equal 2.236, so that would be the length of this one. And keep in mind, it's almost always going to be the case that one of these side lengths is some weird number. So it's probably not going to be the case that 1 and 2 are, and then we have 3 as the third one. That's probably not going to be it. Usually it's a more weird situation, though there are a few cases where it can literally just be all nice numbers, like a 3, 4, 5 triangle or a 5, 12, 13 triangle, which you can both see in certain problems. Okay, let us use this real quick for a couple of things. A 15-foot ladder leans against a vertical wall so that its base is 9 feet from the wall. How high up does the top of the ladder reach in feet? So just to draw this, first of all, it is a 15-foot ladder. So basically what that means is this would be the ladder. This is the thing that's lying against this wall and this floor. So that'd be 15 feet. And then the base is 9 feet from the wall, so 9 there. And then we're trying to find what this angle measurements would be. This is not the longest side of the thing because the longest side is also always the slanted side. So this here would just be B, we can say. And so then we just write here 9 squared plus B squared would equal 15 squared. So therefore it has to be 12 for that one. So B there. This one, you may think this is an unbelievably difficult problem, but it's actually not even that hard because here's what's going on here. We have this whole rectangular crate. So it's a 3-dimensional object. I have a full video on area and volume if you want to see that on the channel as well. But it's asking us, what is D here? And D is the distance from this point down here at the bottom to this point up here at the top. So all we really need to do is use the Pythagorean theorem on this stuff. I guess we might have to use it twice, but it's still Pythagorean theorem stuff. First thing we should figure out is what would be the length from that edge of the box to this edge of the box. It's basically the diagonal of the square. Well, if you think about it, there is basically a mini Pythagorean theorem in here because this is 16. This would also have to be 12 because both of these must be the same thing. Again, area and volume stuff. So therefore, we can just go ahead and say 16 squared plus 12 squared must be equal to something, and that it would be 20. Okay, so now we know here that this diagonal thing in the middle must be 20. We also already know the height of it must be 21 because it says it over here. So 21 there. And then we can just use the Pythagorean theorem again. We can say here this time 20 squared plus this time 21 squared must be equal to C squared. Okay, so that would be 29, and so D would be equal to 29 here. So therefore I go for B for the answer. Okay, you might have thought that that was pretty easy, but here's something a bit harder, SOHCAHTOA. So this is a very, very common thing. This happens all the time. And now we're going to bring angle measurements into the equation, literally and figuratively. So when you have SOHCAHTOA, what this is referring to is a group of functions you can perform on specifically an angle. So we have your sine, cosine, and tangent. Those are the 3 different functions. And the O and H and A and H and O and A refer to what size you have to use to figure this out. So let's say we have this right triangle, and let's say we have a angle at here, and let's just say theta. This is usually the variable that they use to show angle measurements when you don't know them yet. First thing here we have is sine. So you can say here sine of this angle must be equal to the opposite over the hypotenuse. What does that even mean? Well, when you have an angular measurement, the opposite side of it is the thing literally that's just facing across from it. Like if they're both looking at each other, the opposite is the one that is looking at this. So O would be this. And then hypotenuse, as I already have kind of hinted before, would basically be C in the Pythagorean theorem. It's the longest side and also usually the slanted side of the triangle. So that'd be H here. So the sine of this angle must be equal to O divided by H. So let's say we know here that this is a 30-degree angle, that this is a 3 length side, and we're just trying to find what H would be. We could write this by saying sine of 30 degrees is equal to 3, which would be the opposite, divided by H, and then make that tilde. The one thing we have to do whenever you're doing a problem like this is we have to go in here and switch to degrees mode. Desmos is going to automatically be in radians mode, and if you are in radians mode, it's going to mess up all your problems with SOHCAHTOA, so always make sure it's in degrees mode when doing a problem like this. Okay, so therefore we know here that the hypotenuse must be equal to 6. Okay, let's just go over the other one real quick. We have here A, that stands for adjacent. So this is the opposite, this is the hypotenuse. A would just be the one that is left. So this here would be the adjacent side. It's also basically just the one that is not the hypotenuse, but that's right next to the angle, but you can just remember it as it's the one that has no other real function besides being adjacent. So that is how it works. And so cosine of an angle would of course just be equal to the adjacent over the hypotenuse, and tangent of an angle would be equal to the opposite over the adjacent. Now, a couple of quick things here. All you need to know is how to do this exact formula. You don't need to know anything here about like doing -1. You may have seen this like inverse sign before. You don't need to do that anymore because Desmos can just literally do that for you when you write this in. So you can just put sine of 30 equals that. It will solve for you whatever this final measurement is, whatever it is. We also may be in situations where we know what the sides are, but just not the angle measurement. So we could put something like this. So now we see here that this must be a 22-degree angle if we have opposite being 3 and then hypotenuse being H. Now, one thing that I really want you to promise never to do is to ever just take the sine of the lengths themselves. So for example, if we had here opposite and hypotenuse being 3 and 8, you cannot under any circumstances do something like sine of 3 divided by 8. That is not how sine works. Sine is referring to something only on the angle measurements themselves, not the side measurements. The only thing you can do would be saying something like sine of some angle x must be equal to 3 divided by 8. That's all you can do. Never do the functions on the measurements themselves. That's just a way to lead to disaster pretty much every single time. And the last thing is, I have a lot of students who tell me that they're always thinking, okay, can I use SOHCAHTOA on this? Can I use SOHCAHTOA on this problem? Will SOHCAHTOA work here? The thing you should know about this is that you really only use SOHCAHTOA when there's both a side measurement given to you and an angle measurement. It's really the only time you even can use SOHCAHTOA. If you are just given sides, like in this problem over here, you really should not even be worrying about SOHCAHTOA because it's almost definitely not going to be the way to solve that problem. So just focus on it when you're being given sides and angles. Okay, let's get on some practice problems. So we have here this right triangle and it has all these different things, so all the locations of them. It says let this thing be the angle between OP and the positive x-axis, so it'd be this angle. What is the value of tangent of that? Okay, so pretty simple. The tangent would be equal to the opposite over the adjacent, in case you already forgot. So opposite would be this one, and then adjacent would be this one. Okay, so opposite here, this is equal to 6 because we have 6 different boxes. So 6 divided by adjacent, which would be 10 because we have 10 different boxes. So 10, and I can just say here is equal to tangent of, let's just say x1 for that. Okay, so tangent of 30.96376. But you may have noticed here that it literally just says what is the value of tangent. So we actually did not even need to find the angle measurement. I just did that for you so you could see how it would work. All we actually need here is the 6 divided by 10th part, because that is what the tangent would be equal to, 6 divided by 10. So out of these choices, we're just going to see which one is equal to 6 divided by 10. It would just be 3 divided by 5. Yes, that is equal to 6 divided by 10. Both is equal to 0.6. So therefore, A would be the answer here. Now for this one here, right triangle PQR, where angle Q is the right angle of them. It says tangent of P is equal to 3 divided by 4. Now remember, tangent is opposite over adjacent. So if you have angle P here, opposite to that would be this, and then adjacent would be 4. Now the thing that you should know though is that this is not necessarily true. This is something I also see all the time with students when they're doing sine, cosine, tangent. They always just assume that it literally is exactly this number. But you see, that's kind of like misunderstanding what math is. This is not literally the number. This is just a ratio. So what this is really saying is that if you divide this side divided by that side, it's going to equal a multiple of 3 divided by 4. So think about this for a second. It could actually be something like 9 divided by 12, or it could be something like 15 divided by 20. All of these would equal the exact same thing as 3 divided by 4, 0.75. We just know that it equals that ratio in the end. So we don't know that these are exactly 3 and exactly 4. It could be 15 and 20. It could be 9 and 12. We just know that that is the ratio. So one way we could show this is just by putting a variable after it. So we could say 3x and then 4x. That's showing here that we don't know what x is. X could be any number under the sun, but we know that the ratio must multiply out to 3 and 4. Okay, it says here, what is the value of cosine of r? So we have r over here. Cosine would be adjacent over the hypotenuse. So which ones of these would be adjacent? That would be the 3x here, and the hypotenuse would be this side over here. I'm going to bring the Pythagorean theorem back into this to just find what h would have to be, and then use that to solve the problem. Okay, so we can see here that it would have to be 5. Keep in mind again that technically it may not be exactly 3 and 4, and it may not even be exactly 5. This is just what the ratio gets you to. So if I was to put it in here, I would just give 5x. Okay, so to solve this problem now, we know it's 3 divided by 5, and so that's going to be the ratio no matter what, so therefore A would be the answer. Okay, so now we have a problem like this. Many students, if they see a problem like this in the SAT, they'll think to themselves, oh my gosh, there's way too many words here, I'm way too confused, I don't know what's going on, let me just give up and move on to the next problem. But in actuality, when you see a problem like this, you can just write down the information, and oftentimes it makes it a lot clearer what's going on, and it may even be like a pretty simple problem, which it actually kind of is for this one. So we have a search and rescue drill with a helicopter hovering above level ground. So let's just imagine here, this is the distance from the ground to the helicopter. From a ground station, the straight line distance to the helicopter is x plus 8 meters. So from a ground station would not be directly below it. It would probably be something like here. So that would be the diagonal. So that would be equal to x plus 8. And then it says the horizontal distance from the ground station to the point on the ground directly beneath the helicopter, that would be x minus 1. And so if you've been paying attention at all to any of the stuff I've said so far, you would know this is in fact a right triangle. Okay, so it says the angle of elevation from the ground station to the helicopter is theta, so that is the thing. So angle of elevation, yeah, like that would be theta. And then the sine of theta is equal to 12 divided by 13. Now remember the rules again, we do not know that they're exactly 12 and exactly 13. We just know that that is the ratio of them. So sine opposite over hypotenuse. So we basically know here that this would have to be 12 times, let's just say y for the variable, and that this would have to be 13 times, let's just also say y for the variable. And now all we need to do is just use all the information we've learned so far and make some equations with these numbers. The first thing we probably can just do is use the Pythagorean theorem again, because we do have the angle measurements. So let me just go ahead and do that. I can say here x minus 1 squared plus 12 y squared plus x plus is equal to x plus 8 squared. Okay, so that's good, but if you've watched any of my videos before, you know this rule about how when you have a variable, you must have the same amount of equations as you have variables. So since we have two different variables here, x and y, we must have as well at least two different equations. So what we can literally just do is take this exact Pythagorean theorem, copy and paste it, and then just instead of this, we can just say 13y and have that be the square thing, because it would be the exact same measurement. X plus y is the exact same as 13y. They're the exact same number. And then what we get when we do all that is we get this monstrosity of a system of equations. I know you might think this is like some kind of alien thing, but in actuality, we have 4 different intersections here, and we just have to choose which one would be the right intersection for the answer. Now, you know the numbers can never be negative, because if it is, you can't have like negative distance between two things. So therefore, we have to go for the positive choice, so 6.625. We're looking here, what is the value of x? The x term in this would be 6.625. So therefore, we just plug in each of these and see which one works. If I try 53 divided by 8, yes, that is the exact same thing. So A must be right here. One more problem here with SOHCAHTOA. Again, I know this looks like it's going to be extremely difficult, but again, not as bad as it may seem. So what we have here, base point at O, and then top point at T. Then we have 2 of these cables. It just says what all this means. A is between that. Yeah, okay. So yeah, we don't really need to read all this because it is literally just what is written over here. I guess the only important thing that you may be confused on, this 20 would just be A to B, so nothing else there. But yeah. So we have x degrees for the angle, and it's saying what is the value of cosine of x. Okay, so this is again going to involve a system of equations. So I'm just going to choose some random variables for each of this stuff just so we can keep it straight. Let's say that this is equal to y. Let's say that this is h, and I guess that's basically it. Okay, just make some equations for this. It doesn't really matter what equations we choose. We just need some kind of equations. Okay, one equation we can do, y squared plus h squared must equal 29 squared according to the Pythagorean theorem. So you can write that. Another thing we know, 20 plus y squared plus h squared must equal 37. Okay, so we have those two, and it's just giving an error here because we have h here and we already have an x. So what I'm just going to do is I'm just going to write this into regression form. If you want to see my video on what regression form is and how to do that, you can check the other video I have on the channel about regression. But yeah, that's what I'm about to do here. We see here when we do that, y is equal to 3.2 and h is 28.82. Believe it or not, this is really everything we need to just finish out and solve this problem. So yeah, let's do that. So cosine of x would just be adjacent over hypotenuse. So adjacent would be 20 plus 3.2, and then divided by the hypotenuse, which would just be 37. So that'd be 0.627, and I would just try to see which one of these gives us that exact same value. Okay, yeah, it looks like A does, so it would just be A. If you're curious why I use 20 plus 3.2 for the adjacent, that's because SOHCAHTOA only works for right triangles. This triangle over here is just some wonky thing with some big obtuse angle over here. It is not a right triangle because it contains no right angle. So we have to use this whole big thing, which would be a right triangle because it contains a right angle here for this problem. Okay, so let's get to some stuff that actually makes a bit more sense. We have something in math known as special right triangles. What these are quite literally right triangles that are a little bit special. They're a little bit special snowflakes. They appear in the same way every single time you see certain cues. It's kind of like McDonald's. Every time we see, golden arches, every time we see, greasy hamburgers, we know this is a McDonald's that we're going into. Because of those cues, we know that this is a McDonald's, and we always know what to expect as a result of that. Okay, so what they specifically are for the SAT is a 30-60-90 triangle and a 45-45-90 triangle. In case you ever forget what these are, they're actually on the formula sheet. So you can just go ahead and look at the top of your screen if you ever get confused or if you get how this works. For a 30-60-90 triangle, you must have a 30-degree angle, a 60-degree angle, and then that 90-degree angle I said before. And then in this example, the side across from the 30 degrees is equal to x, the side across from the 90 degrees is 2x, and the side across from the 60 degrees is x square root of 3. For 45, 45, 90, you just have two sides that are the exact same, and then a side that is that multiplied by square root of 2. And so the thing you know is whenever you see at least two characteristics, you know it is that thing. If I see here that there is something that is x square root of 3 and an x, I know that this is a 30-60-90 triangle because that's the only thing that could work. If I see that there's a 30-degree angle and a 90-degree angle, I know it's a 30-60-90 triangle. Same thing for this. If I see that there are two sides that are definitely equal to each other, I just automatically know it is 45, 45, 90. What you cannot do is just use one of these characteristics to figure it out. So if I just see, for example, that something is x square root of 3 and nothing else, I cannot just infer that it is a 30-60-90 triangle. In fact, many times it probably will not be. So I've had many students who come to me and they're like, okay, I just assumed this was 30-60-90 because that would make the problem easier. You cannot assume, and they're probably going to punish you for it by making it not work like that. So in a right triangle, one acute angle measures 30 degrees and the hypotenuse has length 14, which is the length of the side opposite the 30 degrees in units. So let's say this is the 30-degree one, and then the hypotenuse is 14 over here. Do we have enough information to know that this is 30-60-90? Yes, because it says here it's a right triangle, so we have a 30-degree angle, and this must inherently be a right angle as well. So those are two characteristics, 30 degrees and 90 degrees must be a 30-60-90 triangle. Okay, so then we know here everything else we need to know. The length of the side opposite the 30-degree angle. If we go back to what a 30-60-90 triangle looks like, the thing opposite the 30-degree angle must be x, and then the hypotenuse must be 2 multiplied by x. So what this means is that this must be 7 basically, because we have 7 here, and then this would be 2 times 7, so 14. So therefore, the angle opposite would be d, 7. One more thing that you should know is that you can find bigger shapes that can divide out to be these. So if we have a square, for example, a square has all sides that are the exact same. I know it doesn't look like it for this because I'm bad at drawing and stuff, but yes, all these sides should be the exact same. If this is x, then this would also have to be x. What you can do with a square is you can actually split it into two 45, 45, 90 triangles. Because think about it. The thing that makes it a 45, 45, 90 is if two sides are the exact same measurement. So this would be a 45, 45, 90, and then this would also be a 45, 45, 90. So just remember that can be split like that. Likewise, you can have an equilateral triangle, which I'm not covering in this video, but it's like when you have a triangle where all the sides are the exact same, kind of like a square. So this was x, and this is x, and this is x. For an equilateral triangle, you can actually split it into two 30, 60, 90 triangles. So if I cut it straight down the middle, we can see here that this angle must inherently be 30 degrees. This angle must be 60 degrees. And since this is directly from straight down, this would be a 90-degree angle. The reason why they must be 30 and 60 is because an equilateral triangle automatically has angles of 60 degrees for each individual one. So this is automatically 60 degrees, this is 30 because it's split in half, and then we have 90 degrees down here. So these are basically just two 30, 60, 90 triangles. Last major rule out of these four is the complementary angle theorem. This really does not appear that often, but what it says is that if you have sine of an angle, like sine of x, that must be equal to cosine of 90 degrees minus that angle. And we can just go ahead and even test this right here. If I said sine of, let's just say 6, 7 degrees, we can just take here cosine of 90 minus 6, 7. And yes, they equal the exact same amount for both things. So really it's that simple. For this one here, we have sine of this thing equals cosine of that thing. In the equation, the angle measures are cubed. What is the value of x? This must equal 90 minus this. Again, according to the rule I just said up here. This is equal to 90 minus 4x1 plus 10. And then we get x is equal to 11 here. So the value of x would just be 11. Okay, so the last thing I have here, many people do not include this when they talk about right triangles on the SAT, but I honestly think you should, because otherwise you're leaving out this major section of problems that could appear. Altitudes. What an altitude is when you have a right triangle, or theoretically it doesn't even have to be a right triangle, it could just be any triangle, where you have a line going from the top to the bottom in this kind of configuration, and it does make a 90-degree angle with the base of it like this does here. The big thing here is that you can also theoretically have a bisector, and a bisector is different from an altitude. What a bisector is when you have a line that goes from the top to the bottom, and it cuts these into equal angle measurements, but it doesn't necessarily make a 90-degree angle down here. So know the difference? All we were talking about here is altitudes. You won't really see that much of bisectors on the SAT. Even if you do, they won't necessarily be 90-degree angles, so it doesn't really matter for this video. But they are completely different things. It's kind of like if you search my name online, John H., if you search my last name as well, you will see me there, but you will also see somebody with the exact same first and last name as me who got into like a road rage incident in Pittsburgh, Pennsylvania, is in jail like right now. Okay, and so that is not me. Keep in mind, that is not me, guys, and I'm probably not even related to him. Okay, maybe I am, but probably not. So these are different things. They just both have the name John and the same last name as well. So just like this here, they look maybe kind of similar, but they are not actually the same thing. Okay, so this is what an altitude is. An altitude is when you have a line from the top going to the bottom and it makes a 90-degree angle down here. So you can basically use three different major formulas with them. The first one is h equals 2 times a divided by b. I don't even really think this is that important to remember, but basically what this is saying is h, altitude, that'd be h, equals 2 times the area divided by the base, which would just be the length of this thing. I say it's not too important because I don't think there's really going to be many situations at all when you get given the area and the base and you have to find the altitude based off of that. What you really need to know is these next two formulas. H equals square root of x times y, and then h is equal to length times length divided by base. Keep in mind, these can actually only work if the major triangle, like the full thing, is also a 90-degree angle like it is up here. If it was not a 90-degree angle over there, these two formulas could not work. So keep that in mind, but they almost always will be a 90-degree angle here, so it probably doesn't matter. What x and y are this piece and then that piece. And then the lengths are this piece and that piece, and then the base is just this entire thing down here. People often get this confused when I teach this to them for the first time because they think that this is L and this is L, or that this is X and this is Y. No, just remember that square root of these two things at the bottom, or length times length, so these two divided by B. That is how altitudes work. Okay, and so you can use these formulas just to figure out these problems pretty simply when you get given an altitude. Many people might think that problems like this are extremely difficult, but once you know these formulas, you start realizing, okay, this is actually like almost baby easy. Okay, so for this one here, right triangle ABC, with C being the right angle, and it says here the altitude from vertex C to hypotenuse AB meets at point D. So that, and then splits into two segments, AD, which is 9, and then DB, which is 16. And it says, what is the length of CD? So remember the formula down here, square root of x times y. So we can literally just say here square root of 9 times 16. So it must be 12. That just is literally the answer. C must be the answer. So you can see here, this problem looked like it was going to be extremely difficult, but literally it was just one formula and I solved it. Last problem here for the video, in right triangle ABC with right angle of C, so something like this now. Altitude from C to AB meets it at D again. Okay, so pretty much same stuff as the last time. CD is equal to 6, so we already know that this time. And AD is 5 longer than DB, so we can say this is X and this is 5 plus X. What is the value of tangent of B? Okay, so a bunch of different things that are coming into play in this problem. But let's just use all the stuff from this video so far to figure this out. So first of all, with the altitude stuff, again, it's this formula H equals square root of X times Y. So I could just literally go here. 6 must be equal to square root of x1 multiplied by 5 plus x1. So yeah, literally that simple, so this must be 4. So therefore we know that this thing would be equal to 9, and this would just literally be exactly 4. Okay, so then how do we find the tangent of B? Tangent would be here, so we need the opposite and then the adjacent. So we need to use the Pythagorean theorem on both of these now. So first on this one, this would be 6 squared plus 9 squared equals C squared. That'd be 10.8 something, so let's just say that. And then for this one, it would just be literally 6 squared plus 4 squared equals C squared again, so that'd be 7.211. And then tangent of B would be the opposite over the adjacent, so something here like this divided by this. So 1.5, that would be also equal to 3 divided by 2, so therefore B is the answer. So hopefully you feel like, you're combining infinity stones here. You've learned all these different things, and now basically like almost every single thing up from this video comes into play on this exact problem here. And you really should pay attention to this video very closely because this stuff happens all the time on the SAT. Even when you get to the more advanced geometry problems, this stuff still happens again and again. It's something that just like keeps appearing again and again, and once you know it, it makes all these so much easier. Now onto similar triangles. In this video, I'm going to explain everything you need to know for the SAT about triangle similarity. I'm going to explain what triangle similarity means, how to tell whether a triangle is similar to another one, and also how to solve some of these harder triangle similarity problems when you do see them on the test. As for triangle similarity, here's what you need to know. Basically, the way you can think about this is, let's say you have two identical twins. I have met a few identical twins in my life. And if you have identical twins, people who look exactly the same as each other, have the exact same genetic information for the most part as each other, these people would basically be equivalent to congruent shapes. There are two shapes that are the exact same thing. So if I draw one square and just go ahead and like literally copy that square over, these two squares would be congruent to each other. They are literally the exact same shape in every single regard. But what if one of these identical twins did something to really change how they look? Like, I guess let's be real. What if one of them got a lot bigger than they were at first? So, much bigger guy. I'm not saying there's anything wrong with being bigger, but let's just say they got bigger for whatever reason. Now these twins would not be congruent because one is clearly a lot different than the other one. They would be similar. They have the same overall genetic makeup, but one is just literally bigger than the other one. And that's literally how similar triangles work. There are two triangles that are the same in every single way, except one is just literally bigger than the other one. So what this is going to mean is that their side measurements are going to be proportional to each other. So not the exact same, but based around the same ratio. So for example, we see here 4 and 3. This one here is 6, and 6 is twice as much as 3, so therefore this one up here for x must be twice as much as 4. And that's why you to solve it here, and twice as much as 4 would be equal to, of course, 8. So that's how it works. You take every single thing from the first sides, and then you multiply it by a set number, and that's how you get these sides for all the bigger triangle. And this is exactly how every similar triangle situation works. The other thing you should know, though, is that the angles are going to be the exact same. So if this angle over here were to be 60 degrees, this one over here would also have to be 60 degrees. For the angles, it's the exact same, whereas for the sides, you just multiply each one by the same exact thing. Now, as for how you can use this in problems, you can write it into a proportion format like here. 3 over 6 is equal to 4 over x. So we have here 3 and then 6. So matching those up between the triangles is equal to 4 over x. So again, matching those up. You have to make sure that you match up exactly which ones correspond to which. And I'll talk more about how to do that in a second. In this scenario, you can just put this in there. If you want to, you could put it into Desmos and you would find that answer would be x equal to 8. I also want to just quickly mention that you can also write the ratio slightly differently. If you want, you could have just said 4 divided by 3 is equal to x divided by 6. This would just basically be taking two things from the same triangle, 4 over 3, and then just mashing up two things on the second one. So you could also just go ahead and do this. No real difference. It's still going to give you 8 for the answer. So don't worry about that. You can still do that if you want to. Okay, how can we actually prove that stuff is similar? With the example with the twins, if these people were to actually take a DNA test, they would see that yes, they are identical twins. They are exactly the same in how they look, all that different stuff. How can we do the same kind of thing for a set of triangles? Well, there are basically 3 different ways to do it. You can use side, 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 aka all of the sides are proportional to the other one. You can do side, angle, side, meaning that 2 sides are proportional and the angle between those are the exact same. So for example, it would be something like this for them. Or it can be angle, angle. So that just means that 2 angles are exactly the same. So maybe this one is exactly the same and also this one would be the exact same on both triangles. A couple things with this. First of all, you probably have seen many YouTube videos talk about this exact thing before, and you may have heard slightly different rules for this. You may have heard somebody say something like angle, angle, side, or something like that. I'm not including that just because it literally doesn't matter. If I just say angle, angle, that embodies everything that has 2 angles in it. You know, it's going to be the same no matter what. Likewise, you cannot do angle, side, and then another side. This will just not work for a host of different reasons I don't want to get into. But yeah, it couldn't be the case that you just have one angle over here, and then you have the 2 sides that are like this one and that one. They have to be sides on each side of that angle itself, like this and that. So this would not work, not a valid way. The rest, though, are perfectly fine, and you can definitely use them to prove that triangles are similar to each other. They're like a valid DNA test. Okay, so I'm going to show you some examples. The thing you should know is that whenever you're doing a problem like this, the first thing you should do is set up a visual thing so you can very clearly see which sides are similar to which. You'll see me doing this on every single problem here. The big thing to know is if you're not actually drawing the triangles out in a way that makes sense, it's always going to be very, very confusing and very, very difficult, and you're probably going to be making a lot of mistakes. So try to do that as much as you can, actually write out the stuff shown. So for this one here, we have 2 triangular planes. We have first of all P, Q, R, and then the second one would be S, T, U. Note here, it says that they are congruent. So like with the identical twins example, that would mean they are literally the exact same, not even bigger than the other one. So just literally the exact same triangle, but it should work overall the same because they would, again, have the same angle measurements. So that's the important thing that matters. Okay, so it says here the measure of angle P is 37 degrees. So that'd be 37. And then says the measure of angle T would be 92 degrees. How would you find the measure of angle R over here? Well, the thing to know with this is that since they are congruent, you just know that this angle over here must also be 92 degrees. Because again, that's just how congruency works. It's the same as if they were similar. They would have the same exact angles in the same places. And then if you've watched my other videos, you would know that for a triangle, it must have 180 degrees as the total angles added together. So I can do 180 minus 92 minus 37, and that gives me 51 as the answer. So therefore, R must be equal to 51. Okay, that was good. Let's get it a little bit harder now. So it says here triangle JKL is similar to M and P. It also says that there's going to be a right angle in both of them, so it would be something like this. It says the sine of J would be equal to 5 divided by 13. So what this basically saying is opposite for J would be this, and then the hypotenuse for that would be this. If you're confused about what I just did there, you can go ahead and watch my other video on right triangles I just posted a few days ago. Okay, so this is what's going on here, and if you also watch that video, you would know that you must actually put these as a ratio. So we don't know that's exactly 5 and exactly 13, we just know that those are the proportion for them. Probably not going to matter for this problem, but just so you know, just so you're not confused and stuff. It then says that MN is equal to 39, so this would be 39. Then what is the length of NP? So I'm just going to go ahead and make this very easy for us. We have here 13 over 5, so that would be the proportion there. And then it says 39 over NP. So if we were to set it up in similar triangle format, we could say equals 39 divided by, let's just say N for that. Using that information, we see that N must be 15, so therefore this would be 15. If that does not make sense to you, just try to look at this until it does. You're taking here these 2 sides over here that match up to these 2 sides over here. You can just set an equation like this. I'm just using this regression to make it a bit easier, but I could also just go ahead and do that and make this X there. And then you use that to see where the answer ends up being. That is the answer for the side measurement. Moving on, sometimes you see problems where you have to actually prove that they're similar. So this is kind of geometry type stuff where you have different pieces of information given to you and you have to actually think to yourself, what would make this true? Not just what to do, how would this even be true in the first place? So it says here triangles PQR and STU. So I'm going to go ahead and draw those. Okay, done. P and S are both 40 degrees. It says PR is equal to 6 down here, and then SU would be equal to 15 over here. Is then asking us what piece of information would be necessary to prove that PQR is similar to triangle STU. Well, remember the similarity rules that just went over here? It has to be side, 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 or angle, angle. Out of those, the only one we could realistically do is side, side, because we have an angle here, a side. Obviously, let's just add one more side. And remember the rule, it can't be angle, side, side, so it cannot be this one. So we can just completely eliminate TU and QR from what we're thinking about here. It's all about PQ and ST. It has to be the sides on either side of the angle. Okay, so looking at this, we're trying to find places where that would be the case. QR, so that would be the one that we cannot use, so therefore A is automatically out. PQ is equal to 8, it says, and then ST would be equal to 20. That seems pretty good, but you can also see here that C says the exact same thing, PQ and ST. And also probably not none of above because we do have enough information here. So it has to be between B or C. The way we can decide between these is just thinking to ourselves the ratios. It says here 6 divided by 15, so 6 divided by 15, 0.4. So we have to have a measurement where it would also equal 0.4 for that thing. So 8 divided by 20, yes, it would be 0.4, so therefore B must be the right answer. If we were to go ahead and try C real quick, 8 divided by 16 would end up being 0.5, not 0.4, so this would not follow similarity rules. Question 4 here, I know this is going to look really, really complicated, but it's actually not even that bad. Most of this stuff is just information. So let's go ahead and write this here. We're talking about a canyon here, so Grand Canyon type stuff. Lengths are AB, EB, BD, and CD. So AB would be 1500, EB would end up being 1200, BD would end up being 600, and CD would end up being 700. They say they intersect at B, obviously, and they have the same angle measurement here and over here, which would be the value of X, which by the way is just A to E. So in case you're confused on that, that's what X is. So kind of obvious based off the fact that I'm including this in this video, but yes, these would be similar triangles. But if you just want to make sure, just think about it for a second. We have this angle over here, which according to geometry rules would be the exact same as each other because they're crisscrossing right here. So we have the same angle measurement there, but also we have the same angle measurement over here. So we naturally follow that angle rule. Since their two angles are the exact same, nothing else even really matters. So therefore we just know that they must be similar. Okay, this is where it really helps to write out some extra information because yes, this does work, but it's kind of confusing. You have to kind of like tilt your head. You have to like contort your brain to figure out what is going on here. It's a lot easier if I just go ahead and write it right side up. So if I'm writing these triangles, I could say A, B, and then E. So basically this one turned on, making AE the bottom of it. And X would be over here. And then we have 1500 over here and then 1200 over here. Then we have another one over here. Let me just write the information for that one. Okay, so we have everything. And you can see now, while this would have been really confusing if we were to look at it like this, now that I've positioned it right, it's not that bad. So now we can just go ahead and just literally use similar triangle stuff here. So we're trying to see what is the value of X. We have here 1200 in X and 600 and 700. Let's just go ahead and write proportion with that. So 1200 divided by X1, we can say, equal to 600 divided by 700. So therefore we're getting 1400 for X, and yes, that would be the right answer. Writing the triangles in an easier to look at way is really, really helpful for these problems, honestly. Next one here, we have a triangle where point D is there. Okay, yeah, it just gives us all the information here again, so you don't really need to read that. It's saying, what is the length of E to C? Again, I'm including in this video, so you can probably tell at this point, these would be similar triangles, but if you want to prove it yet again, you can just look at, if we separate the triangles into this smaller one and then this bigger one, would they be similar? Well, they have the same angle over here for A, obviously, the same angle both times. And also, if we think about it, according to geometry rules again, since we have these two lines that are both parallel to each other, as they say here, we know that this angle must equal the same thing as that angle. Again, that's just like a small geometry rule. I'll probably try and make another video talking more about that. But yeah, just something you can know. If they both are parallel, you have something like this, they must be the same angle. Angle rules yet again, so therefore they must be similar. So we know they're similar now. Let's go ahead and actually write the thing for it. So what you can just go ahead and do in this situation is write 9 divided by 12 and then is equal to 6 divided by x1. That is a completely valid way of doing this problem. I will say though that just to be absolutely certain, I would recommend doing it more in the case 9 divided by 12 is equal to 6 plus 9 divided by this, just to be absolutely sure, because that wouldn't technically be right according to the rules. Like, this thing here would not be a whole triangle, that's just like a trapezoid. So just one small thing to think about, but otherwise, it's going to give you the exact same answer. So 20, it says there, 20, if that is equal to this entire thing, and we have 12 already, then this would just be 8, as we saw there before. So therefore, the answer would be 8, of course. One more quick example. So we have a 5-foot-tall student that casts a 4-feet shadow, so something like this. And I know it's not really a full triangle, but yeah, let's just pretend like it is. So just write a imaginary line there. And then we have another thing that casts a shadow that is 68 feet long, so a lot longer over here. And we're trying to see here, what is the height of that? So we could say x for that. So not exactly a triangle like I said before, but you could just use the exact same stuff here. So 5 divided by 4 would be equal to x1 divided by 68. Therefore, the tower must be 85 high. A couple things I just want to quickly show you guys before we end off today. Here are two very common similar triangle arrangements you will see on the SAT. If you see anything exactly like either of these two things, you just know automatically that they are going to be similar triangles. For this one over here, you can think about it like this. This triangle would be similar to this triangle, which would be similar to the whole bigger triangle as well. So they're basically 3 different similar triangles here. I don't really want to go through the time to prove it, but yes, if you look at the angles, you will find that they are the same angles, and that makes it work. Okay, so this would be a set of similar triangles. Likewise, this is another example of that problem I just showed before. You have this exact angle that would be the same on both this smaller triangle and the bigger one. Likewise, since these lines would be parallel, at least hopefully they would be, you would have the same angle measurement there and there. So 2 similar triangles here, and then 3 over here. I just want to go ahead and solve this problem real quick because this is like a quirky, interesting problem you can see, and solving with similar triangles. Not the easiest way to go about doing it. If you watch my right triangles video, you'll see a much easier way with the altitude rules, but it's just a good exercise to practice doing it. So if you do see something like this and you, for some reason, cannot use altitudes, you could use this instead. Okay, so let's go ahead and start by writing out all the different similar triangles here. This will take a second, but trust me, it'll be worth it, and you don't have to wait for it because I'm going to edit this out. Okay, here are the 3 different similar triangles you can see here. So this one over here would be the one on the left, this one would be this one over here, and this one would be the bigger one if you look at everything all together. Just honestly take a second to think, does this make sense? This is something that's really, really confusing for most students when I show it to them for the first time. Like genuinely, a lot of students look at this and they're like, I have no idea what's going on here. So genuinely pause the video and just make sure you understand what's going on here. It is exactly what I just said, but you may have to just like look at it for a second to really think about what's going on. Because basically I take this triangle, just use it regularly, and then this one I kind of just like flip it over that way, and then this one over here, it's like I completely like flip it out of the page into it. So that is what's going on here, but those would be the 3 similar triangles here. Another way you can just go ahead and think about this is the size of each side. So we basically have a smaller side here and a smaller side here based on these individual triangles. Then you have a longer side for this one over here and a longer side for this one over here, again with each of these respectively. And then for the big one, you have a smaller side here for the base of the entire thing and a longer side here for the entire thing as well. So just another way to think about it. Hopefully you get it by now though. So at this point, we have almost everything we need for the problem. The one thing I'll just do real quick is since we have 2 different side measurements here, we can go ahead and use the Pythagorean theorem on that. So 6 squared plus 8 square that as well equals c squared. So we know that this big one must as well be 10. You'll see why that's important in a second, in fact right now, because we can set a proportion here. 8 divided by 10 would be equal to w for wy divided by 6. And there's how we get 4.8, which would in fact be the measurement of this, and therefore would be the answer for this problem. So similar triangles rule the day yet again, though I will say for this problem, there was an easier way to solve with altitudes. Check my other video if you want to see that. And just remember this, I already showed an example, so not really any need here. One last thing I just want to quickly show you guys before we end off this video. This is something a lot of people really don't include in this stuff, but I think it is important because you could see a problem like this. Is what is known as the angle bisector theorem. So if you have a format like this, you know that AB over AD would be equal to BC over DC. Let me just explain what's going on here. It is not that just if you see a format like this, they must be similar. That's not what I'm saying here. I'm saying specifically if you have a bisector as the line here, this would be the case. When I say bisector, I mean a line that separates an angle into 2 of the exact same angle. So we have here 45 degrees and 45 degrees. Since that's literally the case, then you can use this formula. If these were different things, like if this one was only 30 degrees, you could not use this formula, would not work, would give you the wrong answer. So just keep that in mind. If it is exactly like this, you can go ahead and use this formula. Speaking of which, here's a problem like that. So I'm just going to go ahead and solve this really easily. So 12 divided by 8 equals 18 divided by x1. DC would be equal to 12. Yes, that is the answer. I'm just going to go ahead and teach this as a rule, so you don't need to know really the reasoning behind this. Just know if there is a bisector, you can use this exact way to solve it. Next up, I want to briefly just talk about perimeter and density. This is a very, very simple thing. I'm not even going to spend very much time on this at all. It's honestly just so basic that I just want to throw this in here so you understand it and not say too much else. What perimeter is if you take any kind of two-dimensional shape, so any shape like these, and then count up the lengths of all of these sides of the shape and add them together. So for example, with this rectangle here, if this side is equal to 3 and this side is equal to 1, and then this one will also be 3 and this one will also be 1, you just add these together. 3 plus 1 plus 3 plus 1 would be equal to 8, and therefore 8 is the perimeter of this rectangle. Even for a shape like this triangle, if all of these were, for example, equal to 5 for the lengths of each of them, you can just add up 5 all of these different times. Okay, honestly, that took a while, but yeah, there would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different 5s. So therefore, 10 of 5, 5 plus 5, 10 different times, that'd be equal to 50. So that would be the perimeter of this shape. Then last thing here, a circle. So I know this kind of like, violates the rules of like science and stuff, but those circles don't technically have any sides. The way you can think about the perimeter of a circle is this thing known as the circumference. I also talk about this more in my circles video here on the YouTube channel. But basically the way this works is the circumference is just if you took a circle and then kind of like pulled it apart. So if you have the circle like this, and then you just like kind of unrolled it, so now it becomes a straight line, that would be what is known as the circumference of the circle. And so that's just like a number that you should just know. Like they'll either tell you what the circumference is, or they'll make you calculate it using the formula, which I talk about more in my circle video. So for this, if you considered this aside, it would just be one thing. So maybe the circle has like the circumference of like 34 or something like that. It is unlikely that you're going to see a problem that literally just asks you what the perimeter of a shape is, unless it's like a very baby easy problem. More likely what's going to happen is you might see this just like as a throwaway detail in a longer problem. Like they may ask you a bunch of other information, and then the final thing at the end of the problem would be like, what is the perimeter of this shape considering all these different factors? Second here I just want to mention is density. This is something that, I'll be honest, I've not even really seen on the SAT, but I've heard from other people that it could show up, at least in very rare situations. What this is referring to is basically how packed together stuff in a thing is. So if we think about two different boxes here, and if you have one box with like a bunch of things that are really spread out like this, and one box with everything really, really closely packed together, this would have a much higher density than this one. And so you might be getting ideas here from like chemistry, science, and that's completely fair. Like density is a chemistry, science-based topic. It's not really something that you're going to often see just in regular SAT math or something like that. The way to calculate density is you do this thing, density equals mass divided by volume. Mass refers to basically the overall size of the shape. Not exactly, it's not a perfect definition, but kind of. And then volume refers to how much space the shape takes up. For volume specifically, I talk about it more in my area and volume video on this YouTube channel as well. And that's really it. I don't want to spend much time on this at all, so let me just go ahead into some quick practice problems on perimeter and density. The perimeter of an isosceles triangle is 50 centimeters. Each of the two congruent sides is 4 centimeters longer than the base. What is the length in centimeters of the base? So this is probably like one of the harder problems you can see. Like I said before, this is not just asking the perimeter, it's giving you some other information. So if you have an isosceles triangle, both of these sides would be the exact same as each other. And this has the perimeter of 50, so if we add together all three of these sides, we get 50 as the answer. Then we get this extra piece of information. Each of the two congruent sides, so this one and that one, is 4 centimeters longer than the base. So we could basically say here 4 plus b for that one, and then also just 4 plus b for this one. And then we have b here, the entire b at the bottom. And so this is how this triangle must look. And so you can probably tell now, you can just go ahead and use Desmos and write this as an equation and use that to figure out the answer. So it would be something like this: 4 plus b plus 4 plus b for each of these sides plus regular b is equal to 50. In case you did not know, this means equal to, and then therefore you get 14 as the answer for b. So yeah, the base is 14, therefore we go for b. This one here, we have a solid rectangular block with the dimensions 8 centimeters by 5 centimeters by 3. The mass of the block is 336 grams. What is the density of the block? I explained this more in my area and volume video. Again, I feel like I'm saying that a lot, but yeah, it's something that's really area and volume based. But to find the volume of a rectangular block, you do the length times the width times the height. So the volume of this will literally just be 8 times 5 times 3, so 120. And then we have the mass here already, 336 grams. It's saying grams per cubic centimeter, so therefore we can just go ahead and immediately use the units here. It would be very unlikely that they would switch units on a problem like this because that's not really the main goal of the problem. So I would go here something like Mass over volume, 336 grams divided by 120 gives us 2.8, so therefore B would be the right answer here. Okay, now I'm going to focus a little bit on area and volume specifically and everything involving this. In this video, I'm going to explain everything I know on area and volume problems on the SAT. The thing with area and volume problems is that they look very, very simple on the surface. It's like if you watch a movie like Obsession, like it looks like it's a very basic, simple concept, but you really quickly realize that there's a lot more to it than you maybe thought initially. Like if you watch Obsession, you start to realize, okay, this isn't just a movie about some random wish. The key thing you need to know about this is how each of these work. Now, when I say area, I want you to think of it basically like this. Let's say you have a pancake, and you're trying to think to yourself, how big is that pancake? That is literally what area is. It is put simply, the area within that pancake would be considered the area of that pancake. And so this thing works for any kind of two-dimensional shape. When I say two-dimensional, you can think of it like Super Mario Bros., the original one on the NES. It's something where it's just like a flat surface in front of you, or like a pancake. So if I were to draw this would also be a two-dimensional shape. I could draw this as a two-dimensional shape, and the interior of each of these would be the area of it. Surface area works slightly differently. Surface area works for three-dimensional shapes. Like if I was to draw something like this, think about it like Ocarina of Time on the N64. So more dimensions to it, put simply. So this would be a three-dimensional shape, and the surface area of this is essentially the area of each of the different faces of it that is exposed to the outside world. Keep that in mind, exposed to the outside world. That's going to be important a little bit later on in this video, but all you need to know right now is that, for example, for this cube, it would be the area of this plus the area of that plus the area of this, plus there's three other sides to this cube on the back of it that we cannot currently see, but that are there. So we'd add all of those six together, the areas of each one, and that would be the surface area of this cube. And of course, this works with any three-dimensional shape. We could have this here a cylinder, and the way this would work is we would take the area of the middle part of the cylinder, like this whole thing in the middle, then we would add the area of each of these two circles on each side. And that together would be the total surface area of the cylinder. We could have any shape you wanted to as well. It could be a pyramid, it can be a cone, all this stuff. And the last thing you need to know with all this is then volume. Volume is also for three-dimensional shapes like this, but it just works slightly differently. The way volume works is basically how much water you could put into that shape without it overflowing. So if I was to take this cube and I was to fill it with water, we would basically be seeing how much water can we actually put in until it eventually overflows and everything falls out. That is what the volume is, the amount of water. And that may sound like kind of a weird way to describe it, but actually it's pretty much the best way you can, because that is literally what it is. It's the amount of space contained within the thing. For this same thing, if I put water in the cylinder, how much water could we put in until it eventually overflows? That would be the volume of it. So now you know each of those three things, but how do you actually use it on the SAT? Well, thankfully on the SAT, you get this formula sheet. This is unbelievable. It's crazy that you get both Desmos and this formula sheet on the SAT, but yes, you do get this. So this gets a lot of the information that I just went over on it. You can see all these different shapes and how you'd find the area or the volume of each individual one. However, you may notice that there's one thing that is definitely missing from this list, which is surface area. So that is the one issue with this thing. They don't actually tell you any of these surface areas for any of these shapes. So when you have a surface area problem on the SAT, you're going to have to be able to use this exact logic that I gave up here. Well, not the volume thing, but the surface area thing, and then use that to figure out on your own what the surface area of that object would be. We'll see a couple of examples of that in a second, but it's actually not as bad as it may seem if you actually know how this stuff works, which you now do because you've watched this video. The way that most of these problems work on the SAT is they give you some information and you have to make an equation based off of the stuff shown in this table here, or off the surface area stuff. So for example, for this one, you have a right circular cone with a volume of 216. The height is that, and it says, what is the radius? So first we have to look, what is a volume of a right circular cone? Well, as shown in here, a cone would be this thing here. So 1/3 pi r squared times h. So like that, 1/3. And it says that would be equal to 216 centimeters. So I can say equals to 216 pi. In case it wasn't already obvious, pi is just this random, like, crazy number that somebody came up with a bunch of years ago. You can write it on Desmos just by writing pi, literally that, and it shows as pi. So that's what I'm saying when I say pi. Okay, we have this now, and then it says the height of the cone is 3 times the radius of the base. So you can also put in this information as well. So I can literally go ahead and erase that h and make it, let's say, make it red now. And then I can say r and then 3 times r, because it's saying it's literally equal to just 3 times the radius. So there's no reason why I can't just put that there instead. And so now we have this full equation. And if I pull out Desmos here and just put in this exact equation, you can see here they give you the answer, which would literally just be 6 for this. So the answer for this one must be 6. Pretty simple what I just did there. Now that you know the formulas, I'm just putting it in and I'm using Desmos to find what the answer must be based off that. Here's some more examples. Let's say you have this here, we have a triangle, and we don't have actually the question here, I forgot to put it in there, but they're asking you what is the shaded region? What is the area of the shaded region? The way we could do it for a problem like this is first, let's just find the area of the total triangle, then let's subtract the area of the smaller one at the top, and then whatever is left must be the shaded region. That's the rest in here. Area and volume are both addable, subtractable, like that. So if I was to go over back here again, what is the area of a triangle? It's 1/2 base times height, with base being this thing at the bottom, height being the place at the bottom to the top. So if I was to write it for this triangle here, we could say 1/2, and then the base of this bigger triangle, we go 1 to 12, so 12. And then the height of it, we would just look at this point of the triangle and then go straight down. So we can see here, this would be 9, so just 1/2, 12, 9. If I put into Desmos there, I can see 54 would be the answer. And now all I need to do is just find what would be the area of this smaller triangle at the top. So pretty much similar stuff, 1/2, and then the base of that one would be 1, 2, 3, 4, so 4, and then multiplied by the height 3, so that time it would just be 6. Then I can just go ahead and do 54 minus 6, so answer is 48. So this thing here must be 48 by extension. Here's a simpler one. A right triangle has legs measuring 9 and 12. What is the area of the triangle in square units? How this would look if I was to draw like that, when it says legs, that means this would be 9 and this would be 12. This here would be the hypotenuse because that is the longest side of the triangle. So again, 1/2 times base times height, so 1/2 times 9 times 12. Same answer as the other problem, 54 for this. In case it wasn't obvious, for triangles, when you're finding the area, this means the same thing as the base here, and this would mean the same thing as the height here. Triangles are kind of crazy because none of these specifics really matter too much. As long as there's something that's a base and something that's a height, it can work out. So keep that in mind. Here's another one that's going to require an equation. So we have a right circular water tank with an interior radius of 5 feet, and it's currently filled with water to a depth of 12 feet. It says it can add 600 pi cubic feet of water before it is completely full. So this is going to take a pretty in-depth equation here. So circular tank, that would essentially mean that this is something like that, like a cylinder. So pi r squared times h would be the volume for this. So we can go ahead and write that pi r squared multiplied by h. And then let me just go ahead and fill in each of these with the stuff that we've been given. So we first get given that it's 5 for the radius, so I could put in essentially 5 there for that. And then it says to a depth of 12 feet, that's the current height of it. So I could put it in there for that, I would say 12. And now the other information they're asking is they say that you can add 600 pi to it, and then only then will it actually reach the top of the thing. So let's just go ahead and first solve this. So we do pi times 5 squared times 12, and then we add 600 pi to that. So we get this 2827 number. So that would be what it equals to. But that would not be the answer to the thing, because it's asking us what would be the interior height in feet of the tank. So now we can make another equation using this exact same thing. So remember, pi r squared multiplied by h, and that's equal to 2827.43. I would now go ahead and take this and I can just make another equation. So we know already that it has to be 5 for the radius because that is how it was before. That never changes. And so I can go in here, put 5 down for that, and then just solve this equation. So the answer here, we have 35 point like a bunch of 9, so that basically is trying to say 36. So therefore the answer here would just be D. In case it was not obvious already, the radius for problems like this refers to when you have a circular object, the distance from the middle of that object to the edge of it. So if we have a 2-dimensional circle like this, the radius would be that, how far it takes to get to this piece on the edge. Or if we had a cone like that, it would just be when you take one of the bottom pieces, the same exact thing, how much it takes to get from the middle to the edge over there. This one, we have a rectangular flower bed with a length that is 10 feet greater than the width. And then we have a uniform path of x feet that is surrounding it, and it's forming a larger rectangle with a perimeter of 88 feet. So this is where it gets a little bit harder because now we don't just have one equation, we actually have multiple equations shown here. The first one that we're getting here is that basically it has a perimeter of 88 feet. So 88 would be equal to whatever the perimeter of this larger rectangle is. Now, I haven't gone over perimeter yet because it's not really that complicated, like it's just a pretty simple thing. But basically this refers to the length of each of the sides of a 2-dimensional shape. So for this here, we would just take all of this on the outside, add it all together, and that'd be the perimeter. So what this really means then is that we have, let's say this is the length of it. So basically length plus 2 times x, because we have pieces on each side. So 2x plus length. But then don't forget, that's the first one over here. We have another side the exact same on the bottom. So let me just add another thing to that. And then I have to go ahead and do the same thing for the widths of each. And each one is going to work the exact same way. We have these core width in the middle, and then we have pieces on either side we have to add. If this doesn't make sense, feel free to leave a comment on this video. I try to respond to every single comment, so I'll get to it if you ask me. Now, this is good for the first equation, but there's one key rule that you need to understand for these kinds of geometry problems. And this is true for all of SAT math, but it's especially true when you have a problem like this. Basically, you need as many equations as you have variables. I talk about this all the time in my Desmos videos on the channel, but here's just another way to look at it. In this example, we have both x, l, and we also have w. So we basically have like 3 different variables here, but we only have one equation. So we have 3 variables and only one equation. That means this thing would be impossible to solve just on its own. So we have to find a way to either reduce the amount of variables here or add more equations. So we need to basically make it so it's like the exact same amount. Like it has to be at least like 3 and 3. Or if we were to reduce the amount of variables somehow, we could say something like just 2 and 2. But there cannot be a mismatch between the two. If there is, it's not going to be able to be solved, at least if there's more of the variables than there are equations. So one way we can reduce this is if we were to put in some of the other information from the problem. It says here that the length is 10 feet greater than the width. So if you think about it, you don't actually even need to put anything in here for the L. We can just completely get rid of that. And instead we can just replace both of those by saying 10 plus width. So 10 plus width there, and then 10 plus width. That should make sense. That's literally just what the length is. It's just another way to say it would be 10 plus width. So that's good. So now we are down to only 2 different variables, which are x and w. So a little bit better there, but we still have only one equation. If we're looking at the tally here, we have 2 variables and only one equation. So there's still a bit of a mismatch here. So we have to find a way. Let's just go ahead and add another equation. And a good one to add would be the area of the path being 288 feet. So I can say here 288 is equal to the area. In case you're not familiar yet, I can go and look over here. For a rectangle, it would be length times width. Pretty simple. It's like the easiest one for that. So I can just take what would be the length of this. Well, as we already said, it would be basically just like one of these pieces because yeah, it's 2x plus the whole 10w thing. And then let's just multiply by the width, which would just be exactly this. But what you may notice is that I actually made a mistake here. 288 square feet is the area of the path alone for this. What we have here is the area of the entire thing altogether. So what we can basically do is we can just say this would be the area of the path and then add back to it the area of the stuff in the middle as well. What that would equal to is just length times width for the middle thing. So we can just say here w times, it would just be 10 plus w. Okay, so that we don't add any kind of other variables here by doing that. It's a pretty simple change. All we're doing here is we don't want to just use the outside path. We're also adding the inner path as well. Add them together, and that should be the total area here. What I can do next is just put this entire thing into Desmos and then solve it through that. Keep in mind here, I replaced w with y just because when you solve it easily like this, it doesn't let you just put in a number like w. Otherwise, it can give you an error like that. So I have to put y in here, but that's fine. So then all we have to do next is just see where they intersect in the graph. I'm going to have a Desmos video coming out pretty soon that's going to go a bit more into depth on how this works, why this works, all that stuff. But just know it's the intersection point for the solution for a problem like this. The question that it asks here would be the value of x. So we just have to see here what would be the value of x. It says here it would be 4, 9. So 4 would be the answer here. I know I kind of just taught you area and volume like a second ago. I'm now immediately throwing you into the deep end with a problem like this, which is really hard. But actually it's useful to understand because all the exact things I explained earlier on in this video just apply in a slightly more complicated way to this problem here. Same thing here about area, adding different areas together, setting up equations. It's just doing it with 2 rather than 1. If you have any questions, feel free to leave a comment again. Real quick, I want to show you this pyramid problem just because this is a problem type that a lot of people really get confused on when they learn about area and volume for the first time. So just to go over this, let's say we have a right pyramid with a square base. When they say that, that means they have a pyramid like this. And just when you have the base, both sides of the base, or like all sides of the base, must be the exact same as one another. So then here's the hard part about this problem. It says its slant height from the apex to the midpoint of a base edge is 13 centimeters. So there is a difference here between regular height and slant height. For the regular height of a pyramid like this, it would be if you go from the bottom and just draw immediately up to the top. That's the regular height. The slant height is if you go from the top of it and then go diagonally down the pyramid like this and stop over here. That's the slant height of this. So you have to know the difference. It's very important to know the difference when you're solving problems like this. So yeah, it says here that the slant height would be equal to 13, and then just the regular height would be 8. So pretty good stuff. What is the surface area of the pyramid? Well, first let's just figure out what the surface area formula would really be here. If we look at the area of each of the different sides of this, we have this big square at the bottom. So we could basically just say here, if this is, let's just say this is W and this is also W, we could say it must be W squared plus 4 different triangles. So there's 1, 2, 3, 4 triangles, and each one has the area half times base times height. So it'd be half times the base of it, which would be equal to the width. So, just like the exact same thing you would expect. This is the base. And then the height of it, which in this case would be the slant height. That's where it gets a little bit interesting. It's not going to be the regular height. It would, in fact, be the slant height. And then also we have to do this all times 4 because there are 4 different triangles. So this is the formula, but how would we go about actually figuring out any of this? Well, believe it or not, there's actually a very simple thing we can do here, which is use the Pythagorean theorem. I have a whole video on the channel that talks exactly about what the Pythagorean theorem is, how to use it, all that stuff. But just for a brief overview, you can only use it when you have a right triangle in a shape. We do have basically a right triangle here. If you think about it, you have this, half of the width, then the regular height, then the slant height. That basically makes a right triangle, you can see here. So we could literally go ahead and write here. We basically have W divided by 2. Keep in mind, I have to do divided by 2 because we're only thinking about half of the width. It's not the entire width all the way around because we're just looking here at this one slice of it. So divided by 2, we do that entire thing, then squared. Then we do the height of it, which would be 8, so 8 squared. And that must be equal to the slant height squared, which is 13 squared. So therefore, the width of this must be 20.4939. Good stuff there. And then we have everything we need to finish off this problem. We can just plug in this exact thing and see what we get. We get here this answer 952.84, so we could just write in here 952.8. I think that's all the decimals you would get on the SAT. So the only confusing part about this is just remembering that you can use the Pythagorean theorem in a pyramid problem. That's something pretty much every student forgets when they're solving a problem like this for the first time, or maybe they just don't know, that they don't realize. But yes, these problems can use the Pythagorean theorem, and you could also use the Pythagorean theorem if it was a problem with a cone. So a cone works the exact same way. What a cone looks like is basically this birthday hat type thing, like that. And so you can basically imagine here, if you see a problem like this, where you have the base going upward to the height, and then you have something going over here, and then you can again make a right triangle, even though it's a little bit more curved. It just works the exact same way as a right triangle. So just remember that. One more thing with area specifically, you can have these situations where you have a shape within another shape. It's going to look something like this. We have a square here within a circle. And when you have something like this, it may ask you what is the area of one thing, what is the side length of one thing. The big thing you have to understand here is that to solve a problem like this, you need to find something in common between the two shapes. So for this right here, probably the most common example you'll see, one thing that could be in common is the diagonal. If we go have a line down and show the diagonal of this square, this diagonal would both be the diagonal of the square, and it's also going to be the diameter of the circle. If you want to know more about diameters, you can watch my circle video. I just posted it as the previous video on the channel, but that is what would be the case. And one thing you may also know is that this splits this square into two 45, 45, 90 triangles because they both have these same sides over here. So that is basically the definition of a 45, 45, 90 triangle. So if we have something like this, the diagonal of AD is 7 here. It says, what is the length of each side of the middle square? So 7, and if you know about 45, 45, 90 triangles, 7 must be equal to x, if this is x, multiplied by square root of 2. Therefore, x would have to be 4.95. So therefore, the sides of it are 4.95. 45, 45, 90 triangles is also not something I've discussed in this video, but I will make another video on this for sure pretty soon. And also, if you just want to check, you can see here, this is one of these special right triangles. So it's also on the formula sheet. It's just this right triangle that can appear when you have two sides are the exact same and one side just a bit bigger. So a square would match this exactly. We have two sides that are definitely the exact same because it's a square. So that's that. 4 different formulas I have here real quick. This one is the surface area of a cylinder. This one is the surface area of a sphere, like a 3-dimensional circle. This one is the surface area of a cone, like a birthday hat type thing. And then finally, this is the surface area of a pyramid. If you want my honest recommendation, I would suggest memorizing all of these four formulas. And I know you may be thinking like, oh my gosh, that's so much I have to do. Like, how am I supposed to memorize all this? First thing I will tell you is this is really important because on the SAT, you do not want to have to be fumbling through all these different formulas, have to think, which formula do I have to use? How do I make the surface area of a cone or something crazy like that again? You don't want to really have to be doing that. So it's good to memorize these. In fact, cylinder surface area happens all the time. It's really good to have this memorized. Second thing though, it actually is literally not that hard. And I can prove this because I actually did it myself one time. What I did to memorize these four formulas was I just had a piece of paper, I wrote them all down, then I did not look at them again and try to write them down again. It was hard the first time, but then the second time I got a bit of it, and then the third time I really got it, fourth time I was like perfect at it. So it literally can take as little as like 5 to 10 minutes to do this. I would say 5 to 10 minutes is worth it for having the chance to get a question right that you typically would not have been able to get right. This is definitely especially useful for this one and this one. These are the kinds of things where, yes, maybe there's a logical reason why it works. Maybe you could think about it, but like realistically, you probably are not going to be able to realize why the surface area of a cone or of a sphere works the way it does because it is just kind of weird. So memorizing this is very useful. Cylinder and pyramid does definitely help as well, though you can figure this out pretty much logically, kind of like I did for this problem over here. Now that I got that out of the way, what if we glue stuff together? You can have these honestly kind of stupid problems where they take multiple shapes and then they put them together like an art class, and now you have this multi-shape. Now this is pretty simple. Pretty much everything about this is quite self-explanatory. Like the volume of the shape would just be twice the amount of the original because now we could put 2 times as much water in it if we were to try to fill up this entire thing. Cube, you can only put so much water in it, but this one you can put in a bunch of water, twice the amount as the original. Okay, but what about the surface area? This is where the foreshadowing comes in. I mentioned to you earlier that's only the exposed sides of the shape that you use for the surface area. So that's where this matters. Because in this thing here, we had like 6 different sides of each one of these cubes. But now each cube basically only has 5 exposed sides. Now, if this doesn't make sense, what I'm talking about here is the one that I have in red in the middle. This whole side has basically been taken away from the equation. It's been removed from the rest of society like a problem child. And so now you cannot see it at all. So this would be not included anymore in the surface area for these cubes. If you understand what surface area is saying, this should make a lot of sense. If you don't, then you might have to understand that this is the case. And then if you have a situation like this, you can use systems of equations to figure out what the answer would have to be. So you could have something like this. 2 rectangular prisms each have a height of 60 centimeters. So if I was trying to write this, I could say something like this. So yeah, like that. And then the height of this would be 60. We have 2 of them as well, and both are 60. Now, they are finally glued together along a square base. So basically what this would mean is you put this one on top of that one. So hopefully that makes sense. I know it's getting a little bit confusing here, but yeah, like that. And then it says the resulting prism has a surface area of 2513K, and then was a silent. Okay, so let's first think about what the surface area of one of the things would be. Again, not on the formula sheet, but let's just say, let's take one of these different rectangles. If the height is basically the top to bottom, if this is the length and this is the width, what are all the exposed faces? This is actually like slightly more confusing than it may seem, but it's really not that bad. The first thing is we have a thing at the bottom and a thing at the top, which is its length times width. So we could just say 2 times length times width. Then we have things on the side, so width times height, 2 of those as well. So 2 times width times height. And then we also have 2 times length times height, essentially, because we have the ones on this side as well. Pretty good here. You could include this as one of the formulas to memorize if you'd like to. It does make it a bit easier, I'll be honest. Okay, so we are left with this expression here with all this stuff, and it is going to be equal to k, whatever k is equal to. Now, like before, you're trying to reduce the amount of different variables you have here just to make it a bit easier. Let's think how we can do this. The first one is we have a height being 60. So I can just erase all the heights and just make those 60 instead. So really easy, one variable out of the way automatically. Second thing it gives you is that it says here that they have the base that is a square. So what that would mean is that the length and width is the exact same. So I can also just get rid of all the different lengths and just replace those with the widths. And this is pretty good. We now only have 2 different variables. That's probably low enough. The second one is we have the thing here. They add them together. And now the new surface area is 2513 times k. Now, what about the surface area of this? Well, the simple explanation for it would be that it would just be this thing times 2. So like that basically, but remember the rule I just told you before about the side that's now hidden. So basically what you can think of this as is you're taking one base away from both of them. One base, you don't get that base. So the way I could write this is basically if I just remove 1, so I just make this 1 essentially instead of 2. So pretty easy. That's just a very simple way you can think about it. If you wanted to, you could also just think about it like I don't know, just remove this one entirely, just like, this times, this is just one of the sides. Doesn't really matter. All that matters is that it's now 1 rather than 2 for this because we've lost a side. And now we have 2 things we can put easily into Desmos. We have this with the widths and this with the Ks. Pretty easy stuff here. Just so you know, to make this a bit simpler, and because I was worried there might have been some issues with graphs for a problem like this since it's such a complex equation, I went ahead and wrote this in regression form. In my regression video on the channel, you can see exactly how I did what I just did here. But basically what this would be is exactly this, just written in regression form. Okay, so the thing you may notice here, first of all, is that it says they're both equal to 0. We can just think logically, okay, it doesn't really make sense for the width to be 0. It's not like this is an imaginary rectangle. So we can just easily fix that by just saying W has to be greater than 1. Okay, now it's fixed and it gives us the right thing, which would be 10. So therefore the answer to this one would be 10. One last thing before we end off this video, and this is actually maybe surprisingly really important for these problems, is this thing involving scale factors for these different shapes. So I want you to think for a second, let's say you had a cube like this, and let's say each side of the cube is 2. And let's say you just multiply each side by 3. So now for this one, each side is 6. What did we do here? Well, we took each one and we multiplied it by 3. Each side, I mean. And now we just have a cube that is basically 3 times as big. But is it really 3 times as big? Not exactly. Yes, the sides are each 3 times as big. But let's say we were trying to find the surface areas of each one of these. If I found the surface area of this smaller cube, and I was trying to see what do I have to multiply it by to get to the bigger one, I would not just do 3, I would actually do 3 squared. So if we found that the surface area, actually I guess I can just find it. Okay, the surface area of this smaller one would be 24, so I can just go do 24 times 3 squared, and 216 would be the surface area of the bigger one. Now you can probably get what I'm about to say next, volume. For the volume of these shapes, it would be the same thing, except now we would just cube it rather than square it, so do the 3 exponent. The volume of the smaller one is going to be 2 times 2 times 2, so that'd be 8. So I would just do 8 multiplied by 3 to the third. It is also 216. Do not worry, that is not on purpose. That's just a random coincidence that they both end up being 216. It is not always going to be the exact same amount. So that is how this works. I also wrote just a simple explanation here. If you have a cube that's doubled, the volume will increase by either 2 squared, or 2 cubed. And for this one, it would increase by 8 if you're trying to find the volume specifically. When you see a problem like this, the way you always think about it is what is the linear scale factor, aka what would be that 3 number like for this problem, or the 2 for here. And then once you find that, you can just use that number to solve everything else involving the problem. Okay, let me show you an example here that's really good. So 2 right square pyramids, again, back to the pyramids, they are now similar. In case you're curious, what similar basically means is just exactly this. They would be taking the exact same thing, just multiplying it by a certain amount to get to the bigger one. And they say the ratio of specifically the surface areas of them is 9 to 25. So if the surface area of this one is 9, the one of this is going to be 25. And then if the volume of the small period is this, what is the volume of the larger one? Okay, the first thing we were trying to do, like I said before, is trying to find what would be the linear scale factor, aka what would we have to multiply each side by for this one to get to the bigger one. We have this 925 thing. It's kind of a confusing way to write this, but let's think what would that really be saying here? Basically, it's saying if we have 9 as the surface area for the first one, we would have to multiply it by some random number, let's just call it L, to get to 25. And so that random number would be 2.777. So that essentially would be the scale factor for the area. Keep in mind, this is the area, not the regular sides that are being changed here. So we're kind of going backwards now. We don't have the linear scale factor, we just have the area scale factor right now. Then with this information, I can just go ahead and take this, and then I can just say that must be equal to the actual linear scale factor, let's say S squared. And so then, therefore, the actual thing we're doing for the linear scale factor would be 1.67. So that is the actual linear scale factor for this problem. Now, based off that, we can find everything else we need to know. This squared would be the area scale factor, and then this cubed would be the volume one. So for this one, it says 270 for the smaller ones. So we can just do 270 multiplied by, I guess I can just say S cubed. And so that gives us 1250, basically, a little bit of rounding stuff here, but 1250 for the answer for this problem, which would be C. Keep in mind, I went over a bunch of problems in this video, and this video was probably fairly long for you watching it, but this is really only a snapshot of what can appear in area and volume problems. There's a ton of different stuff that can show up for these problems, a ton of different ways you can ask questions. You can think of all kinds of unbelievable ways to ask new area and volume questions, so you will need to do practice with this to really understand what is going on here, to be honest. Okay, now on to circles. How do you solve SAT geometry circles problems? Honestly, these are one of the most complex and weird geometry problem types that you're going to see on the SAT. And actually, it's so weird that I even made a video one time where I specifically just clowned on them. In case you don't know, I'm the one who makes the SAT Gamify, the Minecraft SAT channel. And I actually had this video out one time. It was like a comedy video where I showed different things that can happen on the SAT, and I used Minecraft to show them. So I was like, this is how test day feels like, and it was like a field of TNT. I was like, this is how studying for the SAT feels like. You're like in a bedrock room. It's like super boring. So it was kind of a fun video. I actually took it down because I just thought like it was so cringe that I just did not want the public to see it anymore. But one thing I had in this video was circle problems. And I specifically said in that video, this is what it feels like when you see a circle problem, and I showed like a bunch of creepers walking towards you. So that's basically how circle problems feel on the SAT. They feel like creepers walking towards you, about to blow you up and completely destroy you. So that's what you're trying to deal with this. But thankfully, they are a lot simpler than they may initially seem. In fact, there's just a couple key things you need to understand about circle problems, and once you understand this, they become actually fairly simple, I would say. What you're about to watch is a snippet of a call I recently did in Mission 1400 Plus, which is my premium SAT Skool community. You can watch it and see what I explained specifically on circle problems and all the different tips given in that. Okay, now onto circles here. This is a bit more common, actually. And the key thing you need to know, if you have never seen a circle before, surprising, a circle is this. So we got a rounded shape. Okay, I'm not sure how I'm explaining this. I mean, yes, you know what a circle is. The formula for a circle is this. Now, if you're confused what is going on here, definitely, check, Desmos. I talk about this in Desmos course, Desmos videos, everything. But just for a quick overview, what is being said here is HK would be the center point of the circle. So if I'm writing this into Desmos, HK would be this middle point right there. And to prove to you that this actually is the case, I'll just go ahead and write a random circle. So let's say I want the center point to be at, let's use a grade number, 6, 7. X minus 6 squared plus y minus 7 squared. And I can just choose whatever thing I want. Let's just say equals 5 squared. Okay, does it work? Does it work? 6, 7? Yes, it would be the middle of the circle. So that's proof that this works. You can just put it in and you get that as the thing. Now, if you're curious what this is representing, this would just be the radius of the circle. The radius is the amount of distance, or it is the distance between the middle point and then the edge of the circle. So if I count how far that is, that would be the radius. If you look at this here, the radius of this circle must be 5. I guess if I want to confirm that as well, I could look at here. So yeah, 11, 7. And then if I do 11 minus 6, that ends up being 5. So yeah, confirmed as well. So that's how you can draw a circle. And I'll go into a problem in a second where you have to actually use this formula, but that's the basics of it. Now, what about when it gets actually hard? I want you to think for a second that you just bought like a pizza. And so pizza, it's great. Let me see if I can actually make this look more like a pizza. Say this is the crust. Yeah. Okay, actually, I'm just going to give up on that. Okay, so let's say this is a pizza. And let's say you're trying to share the pizza with multiple people. And pizzas, they have 8 slices for most pizzas, regular pizzas. And so let's say that you have a friend who just went ahead and took 2 slices. Pretty fair. 2 out of the 8 slices have been taken by this friend. So I guess that would just end up being this piece. Think to yourself for a second, what percentage of the pizza was taken by his friend? It's not some kind of genius thing. It's 25%. Your friend ate 25% of the pizza. If you're asking how much of the pizza was taken, that's 25%. If you're asking how much of the crust was taken, it's 25%. Everything is 25%. 2 out of 8 is 25%. Yeah, all that stuff. So let me ask you for a second, what if we asked you, how big is this, essentially the crust of the pizza? How big is this portion specifically of this 2/8 that the friend took? Well, the obvious way you could figure it out is how much is the total circle for the crust, and let me just take 25% of that. Likewise, if I'm trying to find exactly how much space of the pizza that was taken up, again, I can just find how much space is in the circle and 25% of that. So not going to be any genius thing. It's pretty simple. It's just, anything you would logically think of if you're eating pizza. But there's a couple of just random formulas you need to know. So for a circle, the area of it, meaning the total space being taken up by the circle, is this formula pi r squared. Pi, in case you did not know, in case you're not like really big into math, it's just this random number that was discovered a bunch of, many, many years ago because it makes circles work. That's really is why it was discovered. And the radius is what I already explained. So you don't need to know anything about pi. If you just write pi on the SAT and Desmos, yep, it gives you, so pi. And then r squared. So this would be equal to the area of the circle. And then if I want to find the crust, or let's just use the actual term, the circumference of the circle, I would do 2 pi r. That is equal to the circumference, crust, whatever. So back to my example before, let's say that the radius was equal to like 3. Now we have everything we need to actually find out how much of the actual pizza that friend took. Let's first use the area. So pi r squared. Pi, and then we know the radius would here would be 3, so 3 squared. So 28, that is the total amount of the pizza being taken. That is the total area of the pizza. And so if we're looking at 25% of that, I could just literally put in Desmos 25% of that, which would be 7 point, yeah, that stuff. I could also just say here, if I want to, 2/8 of that, which would just be, yeah, 7.06. Likewise, if I want to do the same thing with the circumference of it, or crust, again, you can just do 2 times pi times 3, which would be this, and then I can also do 25% of that, which would be that. So that is the amount of crust of the pizza that this friend has taken. Now, the one other important thing to know here is that oftentimes it won't be a literal pizza. Okay, you probably already knew that. But more than that, you also need to know that they're likely going to give you an angle measurement here instead. So they might tell you that your friend, rather than eating 2/8 of the pizza, they ate 135 degrees of the pizza. Okay, if you're talking about degrees when eating pizza, that's you're kind of cooked there. But for the sake of math, that could be what it gives you. So 135 degrees. Now, keep in mind, what this is saying is that the circle overall, if you count everything, the total amount of angles of the circle always is going to add up to 360 degrees. That's just something you can memorize. Keep in mind, 360 degrees is the total amount of degrees in a circle. So if your friend ate 135 degrees, the logical thing we can just say here is 135 divided by 360, and then multiply that by thing, which would be, yeah, let's say 2 pi times 3. So that is the amount of pizza. Okay, and if I want to do the area again, I could just do pi times 3 squared. These are just like random rules, might appear in the SAT. This is not related to the last part. First thing here is with tangents. So if anybody's ever told you, like, that's tangential to the conversation, okay, I don't think anybody actually says that anymore, but if somebody did tell you that, what they're basically saying here is that you're talking about one thing, and then your friend is like talking about something close to it, but not exactly the same thing. Like, let's say we're talking about, like, I don't know, let's say we're talking about like the economy. And we're saying, the economy is so bad right now. And then your friend starts talking about politics. Those kind of are related. Economy is equivalent, not equivalent, but they're related in many ways. Economy affects politics, politics affects the economy, but they're not the same thing. They're only like, kind of related. And so that's basically what a tangent is. What a tangent is a line that touches the circle at one place, but then literally never again. It doesn't have any other relation besides this one place with the circle. So like this line over here. The big thing you must know, the big thing you have to know about this, the one thing above everything else, is that tangent lines are always going to be perpendicular, meaning they make a 90-degree angle to the radius of the circle. So in this example here, I could, draw this, a right angle here. And that's going to be important because now what you could theoretically do is make a right triangle with this, or actually 2 right triangles, both on either side. And then you can actually use the Pythagorean theorem or other right triangle stuff to figure out stuff about this circle or the area and this stuff, and that's lengths and stuff. So keep that in mind. Tangent is always perpendicular to this. And also remember, it can only go through exactly one point. If you ever see something where like it is a line that goes like this, that would be considered a chord, not a tangent, which I'm not going to be going over in this call, but you likely will not see that on the SAT, so it's probably okay. Now, another thing you should know is inscribed angles. What this is referring to is basically if you have a situation where you have an angle on the outside of that interior angle, you have to know that that inscribed angle is half of the interior one. And this is very unlikely to appear on the SAT as well. I really have never seen this on any actual SAT. I think I do have a problem that I can show in a second that involves this I found from Onico, but as far as the actual SAT, I mean, I've really not seen an actual problem involving this. So unfortunate, but I guess it's okay. Last thing, one more niche rule, just to finish our list of 3 niche rules, is this thing with a triangle within a circle. If you see something like this, specifically if you see something where you have a triangle and it has this hypotenuse, which is the entire diameter of the circle. Diameter is just the radius times 2, so the entire like length of it, then you know that this must be a right triangle. That's just a rule you can know. If it's like this, you know this must be a right triangle. So that's one last thing. Okay, finally some actual stuff here. So this circle has a radius of 8 units. So let me just go ahead and draw that. So, and then what's the area of the sector determined by a central angle measuring 135? Okay, 135, there we see it again. Amazing stuff here. So it says the area of it. So that's going to be the pi r squared thing. So we can do pi times 8, which would be the radius squared. And so this would be the total area of the circle. This is the amount of space the circle takes up. And so 135 degrees, all we would have to do there is 135 divided by 360, and then just go ahead and multiply that amount by this, which would be 75. And then I just have to convert each of these numbers into that. So I can just see like 18 pi. Okay, that's not enough. 24 pi. Yep, that's enough. So therefore 24 pi must be the answer. So not too complicated, just pizza logic again. Now, one like simpler Desmos related problem, say you get given this equation, which lies outside of the circle. So this is going to be very, very simple. Like all I have to do is just write this out and just see which of these points is not within it. So 49, and then outside the circle, you know, I can literally just like type like 4, -2. Okay, that's inside the circle. You can see within it. Then 10, -2. Okay, yep, sure, that's outside the circle. That would be right. These, I'm sure if I tried it out, they would also not be in. Okay, this is another Desmos problem. If you have the endpoints of a circle of those, which of the following could be the equation for it? Similar to the other thing, I can just go ahead and type each of those in. And now I can just check to see, do each of these circles have the same thing as that? So I could do that, and then plus that equals 64. And then if I type that in, plus 6, and then plus 5 as equal to 16. Okay, that's also not it. If I do -6 and then -5, okay, yes, we see here, yeah, that would perfectly match with the thing there. A couple of the problems I didn't have in the original recording. First, this one. In circle P, the minor arc AB has measured 120. The length of this arc is 6 pi centimeters. What is the radius of circle P? So a few different things we have to do here. First, let's just draw what we're given here. And so it says it has a minor arc, which just means an arc. Whenever it says minor arc, it just means regular arc, of 120 degrees. And then it says the length of this arc is also 6 pi centimeters. So we both have the degree measurement and also the length of it. And now we're trying to see here what would be the radius of the thing. So this is basically like the pizza example, but now we're just kind of working backwards, I guess you could say. So basically we know here that if you have 120 divided by 360, that is equal to 6 pi, and then we don't know what the full amount is. So it could be x1. So that's what's going on here, because this full circumference, that's what's being shown by the 360, and that'd be x. So x1 says here is 56.55, so I can do 56.55 there. That is the full circumference of the circle. Now remember as well that circumference is 2 times pi r. So what we literally could just say here is 2 pi r equals 56.55, and then we get r must be equal to 9. Looks like a whole number, so probably is correct. So yeah, 9 is what I'm getting there for the answer. And so yeah, 9 would be the answer. Same kind of thing, we just set up a formula here basically instead of the other stuff that we did before. This is one inscribed angle problem. So if you remember up here, I was showing you how if you have an inscribed angle, the angle on the side is half of the one in the middle. So that's what's being shown over down here. So it says here minor arc AB, it gives us 10 pi. You may not be able to see that, but it says 10 pi for the length of the arc. And it's asking what is the area of the circle. So we're gonna have to do some similar stuff for this one. We just have different information to work off of. So since it says 40 here, what we know is that basically this is the equivalent as if it said 80 degrees in the middle, because that's what's being said with the interior and exterior. So 40 and then 80 degrees. So what we really are seeing here is pretty much the exact same thing as the last problem. 80 divided by 360 tilde 10 pi divided by, I don't know, x1. So we know the full circumference of this is 141.37. So I can then do 141.37 again and do 2 times pi r. We now know the radius is that. And then with that, we can find the area of the circle, which is just be pi r squared, which we get is 1590. So yeah, 1590 should be the answer for this one as well. Just got to remember, if it's on the side, you use inscribed angle stuff. If it's in the middle, you use the regular stuff I already said in this video. Real quick, one with the tangent thing. So if we have a circle here and it has the center of Q, and we have the points R and S that both lie on it. So like that. And then we have a random thing T over here. And then it's basically saying it's tangent to the circle. So it only passes through at one point for both of those, but it does intersect at T for sure. Okay, this one kind of looks bad. Okay, like that. And it says the radius of the circle is 260 millimeters. So if we just do this, that would be equal to 260. And then it says the perimeter is 3880. So I'll just throw this over here because we don't know how it's going to play yet. But when it says the perimeter, that means the perimeter of this quadrilateral. So basically, if we were to draw a line like this to combine all this, if I do this side plus that side plus that side plus that side, it gives us 3880. And now we're trying to answer this one final question. What is the distance between points Q and T? So basically, if we write all the way down here to T, what would that be equal to? So let's use the information we have here and try to figure out some of this stuff. So we know that the radius must be 260. So another way we could theoretically write this is we could just make both of these be 260 because that's what it means. When they are showing this quadrilateral, each one of these is just the radius. And then we have 3880. What we can do is we can take 3880 and then subtract 260 and then subtract 260 again to just get rid of both those radii and then see what we have left. That'd be 3360. Okay, so what are you supposed to do with that? Well, the thing you should also know about this is when you have a situation like this, where you have basically a perfect, quadrilateral being made with a tangent line, this line RT and this line ST will be the exact same as each other. It just kind of makes sense. Like there's no other thing that would change about this. The radii both still must be the same. So therefore these lines must be the same as well. So you can just take the 3360 and since we know the rest of the perimeter must be evenly distributed among them, we can just divide it by 2. So 1680. So now we know that both of these lines would have to be 1680 as well. How can we use this for the problem? Well, what you may notice now is that since we know that there must be a right triangle between these two lines, we can basically just use the Pythagorean theorem. You may have not noticed this at first, but yeah, we have a right triangle here, 260, 1680, and then we have a hypotenuse basically that goes from Q to T, which is what we're solving for. So I can just go ahead and write it out there. So I can say 260 squared plus 1680 squared, and then tilde C squared, so 1700. So therefore the answer here would be 1700. It may look like I was doing a bunch of weird stuff here, but ultimately it was just a kind of a repeat of what we had before. We have a right triangle that's made with a tangent line. Only difference is that we have a quadrilateral, but we just know we separate the perimeter amongst the different sides of the quadrilateral, and then we can just use the Pythagorean theorem, which you should hopefully already know if you're watching this video. Let me talk to you for a second about chords. So this is something that is a very rare SAT concept. In fact, I very doubt that you're actually going to see this on the SAT. But it is important knowledge and it is something that could show up because really what this is just an amalgamation of other stuff I've already said in different YouTube videos. So it's not any kind of like new information here. It's just a more interesting way of kind of applying it. And you'll see what I mean by that in a second. So basically what a chord is not like on the piano, unfortunately. It actually is something like this. When you have this line here on a circle that like doesn't really look right. The way you can think about this is it's basically like a line where if you cut a pizza in that way, you'd be just absolutely, mentally insane. Like nobody would reasonably cut a pizza in this kind of configuration. That's what a chord is, a very weird pizza slice. And so with this chord, you need to just know a couple random facts about it. The first random fact is that if you have a chord like this that's extending off from the center of the circle, if it is split up like this side of the chord is exactly equal to this side of the chord. CB would be equal to BD. And so that's just something you can memorize, you can understand. It's always going to be the midpoint, so pretty much exactly just what it looks like for this chord here. And then the second thing is if you have two chords and they both are the exact same distance from the center, so like this is 3 and this is also 3, then you know that they must literally just be the same exact length. So this is equal to that, which is equal to that, which is equal to that. So really simple stuff there, not really too much you have to memorize, but there's one more kind of important rule that you really should know here, which is that you can actually use the legendary Pythagorean theorem on these kinds of problems. You may be thinking, how is that possible? Well, it's actually pretty simple. First of all, you need to understand that the radius of a circle, basically the line from the center to the endpoint, is the exact same no matter where on the circle you are. So this radius is the exact same as this radius, which is the exact same as this radius, which is the exact same as this radius, which is, same as literally anything I could draw here, that'd be a radius. So with that information, you can just figure out for a problem like this, if you know that the radius is something, you could write a right triangle here. So I could have this be the hypotenuse, these be the two legs, and then I could calculate some piece of information. So for example, if we knew that b to d is 4, we could find out that, Pythagorean theorem at 3 squared plus 4 squared equals c squared, this would be equal to 5. That's just a common Pythagorean theorem thing. Typically, I would actually write it out. And obviously, it would also be possible on this one. If we know that the radius is something, we can just write something like this and draw it out. That is just the one other piece of information you need to know. Besides that, there's no other main things you should need to know for the SAT, at least in the current form of the SAT as of July 2026. So that is it. Here's some practice problems on this concept. We have a circle with a chord length of 24. Let me go ahead and draw that. So something like this. The chord is 5 units from the center, so like that. What is the radius? Okay, we can pretty clearly see what's going on here. So we could just pretend like there's a radius from here to there. It's going to be the exact same as every other radius. And then one other piece of information we have is that with that rule I said above, these both must be the exact same. So I can even just say here that this would be 12 because 12 is half of 24. Then I can just go ahead and use the Pythagorean theorem. That would give us 13 as the answer. So therefore, this is 13 and the radius would be 13. So simple Pythagorean theorem stuff there. This one, a circle has a radius of 17, so something like that. And then a chord is 8 units from the center. So drawing this, there'd be 8 units to get to this chord. And then it's asking here, what is the length of the chord? So I kind of drew this radius in a really bad way, so you could just pretend like it's over here just to make it easier. So 17 there. It's asking what is the length of the chord. So again, Pythagorean theorem time, we can say 8 squared this time plus b squared, because this would essentially be a leg of the triangle. And then that would be equal to 17 squared. We see here 15. That actually would not be the answer though, because that would be for 1/2 of the chord. It's asking the length of the entire chord, so we have to do 15 times 2, which would be 30, because this entire thing. One more practice problem here. 2 chords in a circle are 9 units from the center each. So something like this. If one has the length of 24, what is the length of the other one? This is actually just a very simple question. It uses the exact rule I went over here with both of them being the exact same thing. So the answer would literally just be 24. It is that simple, and that's all you need to know about chords for the SAT. Last thing, I'm going to talk a bit about the unit circle on the SAT. In this video, I'm going to explain everything you need to know for the SAT involving unit circles specifically. The reason why I wanted to make this video is actually because of a post somebody made recently in my free SAT community. Because someone here, I won't say their name, but they made this post and she went ahead and she posted a unit circle problem that she had seen. And you can see here, if you go over here, this got 165 comments and only 4 likes. What does that indicate to you? Well, this indicates that people were really debating this answer very heavily. Just a couple of people were really arguing about what the answer to this question was. So this makes me realize that I probably should make a video on this because a lot of you might be confused as for how you should be evaluating unit circle questions on the SAT. So in this video, I'm going to be covering everything you need to know about unit circle questions for the SAT and how to solve them if you do see one. As for unit circles, the first thing you need to know heading into this is what the unit circle even is in the first place. So I'll be honest with you, I've not really looked at this since like 8th or 9th grade, and for reference, I'm currently graduated with high school. So it's been many, many years since I first learned about unit circles, and I was kind of hoping I would never have to use this knowledge ever again, but unfortunately, we are here and I do. So what the unit circle is basically a simple way, or I guess arguably simple, to figure out what degrees and radians must match up to when dealing with angles. If you're not familiar, you have this thing known as an angle, which is basically the distance of 2 lines when they're arranged in this kind of configuration. So if we have these lines here, the angle measurement would be this, the distance between those two. And now typically it is usually measured in degrees. So this could be like, for example, 30 degrees. But what you may not know is that another way you can write degrees is in this thing called radians. It's just another unit that can be used to describe the measure of an angle. So for radians, it's more just in this format. It's just regular numbers like 0, 1. And you could just say this many radians, 1 radian, 2 radians, 3 radians, 2 pi radians. That is what you would say for that. And just another way of describing the angle measurement. So for example, you could say 30 degrees, or you could say some amount of radians. I'm not sure exactly how much that would be. Actually, I can even check. So yeah, according to this, it would be equivalent to 0.52 radians. Now, if you're confused how I did this, I'll explain to you in a second. But yeah, this is what 30 degrees would be equal to if you convert it into radians. Okay, so yes, we have this list of things where we have the degree measurement and the equivalent radians, which you can get from these two numbers. They're not exactly these two numbers, but they give you the radian measurements. What many people might recommend you to do is just literally to memorize this entire unit circle so you can evaluate it when you get to the SAT. And while that may be arguably helpful, it might save a bit of time. If you don't want to go through that entire process, which I don't think you should have to do, you can also just use this method with cosine and sine. The thing with these is that the cosine of the radians is equal to the x unit of the thing, and the sine of the radians is equal to the y unit of the thing. I know that maybe doesn't make too much sense, so let me actually explain kind of what I'm saying here. If it is equal to, let's say, 3 radians, the cosine of 3 would be equal to the x unit here. So like square root of 3 over 2. And it's not exactly what that's equal to, but yeah, cosine of 3 would be this value here. And then likewise, the sine of whatever number would be the y value here. So you take the cosine or sine of the actual radians unit itself, and that is going to be giving you what these units over here would have to be. Now we'll be drilling a bunch of problems on this in a second, so you won't have to be perfect at this just by learning it for the first time, but just try as hard as you can to understand that concept heading into it. Now, if you want to know how you can remember that cosine goes for the x unit and sine goes for the y, you can just think about a regular triangle. So this isn't, obviously too scientific of a way of looking at this, but cosine, as we know for triangles, as I say in my right triangle video, it's adjacent over the hypotenuse. And so thinking about adjacent, if you have the angle over here, adjacent would just literally be the one at the bottom, which makes sense for x because x is like literally going horizontally. It's going that way and it's going that way. So bottom both times. Meanwhile, sine deals with this configuration opposite over hypotenuse, which would be vertical, of course. This is going upward, so that's why sine is the upward one. Just a way you can remember it. So now let me show you how this works involving Desmos here. So the big thing you need to know about problems like this is that you can go over here in Desmos and click between radians and degrees mode. This is, probably the biggest time on the SAT where you really need to know this fact. I mean, of course, it matters with, regular SOHCAHTOA as well, but for these problems, it's really, really important to understand this. So pretty obvious what you need to do here. If it is dealing with radians, you put it in radians mode, which is what's going to be for the majority of these problems, just so you know heading into this. But if it's in degrees, then you go into degrees mode. So let me show you what I'm trying to say here. We have 30 degrees over here. We see that 30 degrees is equal to square root of 2, 1/2. If I do cosine of 30 degrees, we get this 0.866 number, which would be equal to square root of 3 divided by 2. Yes, so you can see here, here's how it's working. You take the angle measurement, you do the cosine of it, and that would be the x unit. Likewise, if I did the sine of it, we get this 0.5 thing, which of course is equal to 1/2. 1/2 is the same thing as 0.5. So now it should be making a bit more sense. But of course, if you have radians, you can just convert it into this other thing. Instead, you just are going to have to write this in the radians format. So like if you, for example, have like 0.5 radians, you can say sine of 0.5, and this would be the y unit. You can say cosine of 0.5, that would be the x unit. And we'll see some problems on this in just 1 second, as I said. Okay, so let's see this problem. Point P lies on a unit circle in the xy plane and has coordinates of 1, 0. So I would suggest when you see points in problems like this, just immediately write out each one. And you can actually even click this thing label, and then that allows you to put a letter for that point. So you can see here, this is specifically point P. So that is really useful. Point O is the center and has 0, 0. That's what you're typically going to see in, problems like this with the unit circle. So that there and then O. Then you have point Q, which is 0K for its unit. So that is that for a Q. And then K would also have to be a negative number. So we know no matter what, it's going to be somewhere like down here, which could be the positive measure of angle POQ in radians. So just to evaluate what this is trying to say, if you look here at the unit circle, this is basically like if we were trying to take this huge angle going from 0 all the way to this down here. So that is basically what is going on here. So you can imagine that for what this is supposed to look like. And that's what these points are trying to say. So the easiest way to solve it at this point here is that we can just take each of these different things that we get for the answer choices, do the sine and cosine thing on them, and see, does it match up with this K point? Is it somewhere in this kind of vicinity down here? So for example, I can do here cosine of 9 pi divided by 2, and then sine of 9 pi divided by 2. If I put that into this, it's going to make it into a point. And you can see here, this point would be above the thing. So that does not work. It's not in this vicinity down here. So therefore, that cannot be the right answer. A is out. If we do the second one, 5 pi, we do that there. And then for this one, we do 5 pi as well. We see now it's on like this side of it. So again, not where we need it to be. It needs to be somewhere down in this vicinity. So not that. Then we have 11 pi over 2. And we can see, yes, that is now in the vicinity. Theoretically, K could be equal to, let's say, just say like 1, in which case it would be the exact same thing as this green point over here. We know it has to be negative as well, so that's why K cannot like be up here. So we know C has to be the right answer, and if we were to try 6 pi, we get, P, which again would not be the right answer. So just to reiterate one more time in case it still doesn't make sense to you, cosine of the radians amount is going to be the x unit, and then sine is going to be the y unit. That's why I put it in this unit form here. Okay, this one here, we have a unit circle with the center at origin O again, so I can just write here 0, 0, label O. And then we have point A with 1, 0, so there, and the point B with these coordinates over here. And we're trying to see the measure of angle AOB. They say that it is P radians. What is the value of this stuff here? So now you can see we're kind of working backwards. We already have what the X and Y unit would be, and we're trying to figure out what would be the radians measure based off of that. One way we can do it is basically make a system of equations using Desmos regression. So we could say here's something like cosine of P and then sine of P. And then we have to say that these must be equal to this exact thing over here. That should make sense to you if you understand kind of what we've been doing here. We're trying to see what value basically makes both of these true. Cosine would be the x unit, sine would be the y. We see here that the one that makes both those true would be 2.06. So therefore, we can just use that and we can say sine of p divided by cosine of p. That'd be negative 1.875, which would be equal to negative 15 divided by 8. One thing that I should mention is that you may think that you could just go ahead and split these up and say something like cosine of p is equal to like negative 18 divided by 17. That would not work because you have to think about it like there are multiple different values that could all make this exact thing true. You only find the right one when you consider both of the different things. You're trying to find a value where both cosine of p is equal to that and sine of p is equal to this. That's why I have to do the whole thing, because it is a system of equations you need to use there. If you're confused about the Desmos regression stuff there, I have a whole video on Desmos regression you can watch to understand it a bit better. Also, I believe this is the problem that was posted in the community, at least a version of it, so you can use this as a good reference as well. Oh, we have this one here where we have an origin at 0. I'll just go ahead and write that as being 0, 0, because we always know that's going to be about that for these kinds of problems. And then it says it's rotated counterclockwise from the positive x-axis. That's not really as confusing as it sounds, it just says it's like this, like a regular angle. And then it says here that it has, this amount of radians, where this is less than that, is less than that. So a bunch of information here that may seem really important. It's not really that confusing, but we know that the radians amount must be between 6 pi and 8 pi. And then it says it intersects the unit circle at 0 at the point a negative 1/2, where a is less than 0. So I can just go ahead and say here a and then negative 1/2 as well, and then put a slider for a. So what would be the value of A? They actually even just give us the radians. We see here that the radian amount is 43 pi divided by 6. So that makes this problem a lot easier than maybe it would have been otherwise. But okay, let's just think about what we're trying to find here. We're trying to find what the x unit of this would be. So we also have the radians here. So what we can just literally do is say cosine of 43 pi divided by 6 and see what that gives us. We have negative 0.866. We do know it must be negative because they say a must be less than 0, so that makes sense. And then we just go ahead and just see which ones of these match up. There's not really an easy way to do this in Desmos regularly. We just have to go ahead and try it out. So like that. Yeah, actually, just the first one I tried, negative square root of 3 over 2 would literally just match it perfectly. So I can just go with this. Just so I can show it, I just want to show you an example where it involves degrees, at least to a small extent as well. This is not going to be a very hard problem, but just so I can show it. So we have, again, the beginning being at this 0, 0, and they have A lying at 1, 0, and then point B is lying over here. So we have just all three of the points immediately. So good stuff. We have this configuration over here. What would be the measure of angle AOB? We are saying here in degrees. And keep in mind, you can do the exact same stuff as I've been doing in these other problems, just in degrees mode. All you need to make sure is that you're actually using these degree amounts, which are going to be like in the hundreds, whereas radians are typically like, 1, 2, 3, 4. So that is what we can use here. And we can just go ahead and literally just make another system where we could say here cosine of, let's just say, I guess P, whatever, sine of P. And then we have here equals negative 1/2. And then the other one, square root of 3 divided by 2. So we see 120, that is the only angle measurement that works, and we can go for that. I will say for a problem like this, if you did have it memorized, you might be able to save like a couple of seconds. Like you could just look here and see immediately that, okay, negative 1/2, 3/2, that must be 120 degrees. It's just right over here. But I honestly do not think the amount of time you're going to save with that is going to matter too much when you actually get to a unit circle problem on the test. Like probably even just thinking about the problem, having to think, okay, which, remember the unit circle again, which thing goes where, probably that's that alone is going to take you enough time that it wouldn't really be that effective. And speaking of which, it's worth mentioning that this is a very, very rare problem. Like it's very unlikely you're going to see this on the SAT. I've taken multiple SATs where I did not see a problem like this. So you may be wondering why I didn't make a video on it. Well, just because it is so confusing that if you do see a problem like this, you are absolutely cooked if you do not know this stuff. So though there's a small chance, it is very good to know. And I did even have a few people who told me that on the June SAT, they did see a problem like this, at least one of them. So good thing to know that, there may be a potential for seeing this on a future SAT, even if it's not super likely. Okay, so that is it for this video, but as I kind of alluded to at the beginning of this, one thing you really need to understand after finishing this video is if you just finished this video and you didn't do any practice on any of this stuff, I know it may sound cliche because you probably have heard a lot of people say this, but you really have wasted your time. Like genuinely, you have really, really badly wasted your time because none of this actually matters at all if you're not doing practice on the stuff you're doing, especially in a field like geometry. You're not going to see the exact problems from this video on the SAT. I can guarantee you that. You may even see some stuff that's maybe slightly more complex. And so the only way you're going to get the skills for those kinds of problems is by just doing a lot of practice on this different stuff. One way you can get some practice questions is with Mission 1400 Plus, which is my full SAT community, which you can access with the link in the description on this video. What you get in here is over 28,000 practice questions through the program we use called Onico, plus one-on-one support from me to actually help you improve your SAT, plus our full math course and full reading and writing course. We have a ton of stuff here that's really valuable for improving your SAT score, so if you have any desire to hit 1400 plus or higher by your next SAT, definitely join with the link in description below. That is all for me today. I really do hope this video was able to help you and helps you understand geometry and trigonometry a lot better than you did before. Good luck in the SAT and make sure to always stay Gucci. Rest in peace, Oliver Tree.